Hello there, and welcome to Science for Sleep, where curiosity gets cozy, science takes its time, and the universe is allowed to be both fascinating and just a little unsettling. Tonight, we're heading somewhere familiar in name and deeply strange in reality, the far side of the moon. It is not the side with the famous dark patches we know from childhood drawings, and it is not simply the moon turned around. It is rougher, older, drier, more heavily cratered, and in many ways harder to explain. And when a crude spacecraft like Orion swings around that hidden half during Artemis II, the journey becomes something more than a technical milestone. It becomes a very human encounter with distance, silence, and the uncomfortable truth that space is beautiful right up until it reminds you how little it cares about your comfort. Before we settle in, let me ask you something fitting for a night like this. Where are you listening from right now, and what time is it in your corner of the world? Maybe it's late enough that the room has gone quiet and the day is finally loosening its grip. Maybe you're listening under a blanket or in the dim light of a bedside lamp, or half awake on a sofa telling yourself you'll close your eyes any minute now. And if this gentle trip around the moon turns out to be a soothing way to end the day, I'd be very grateful if you liked the video, maybe subscribed, and joined this small corner of calm where we ask large questions in a very unhurried way. Now let's ease into it, because what waits beyond the moon is not a jump scare. It is something slower, stranger, and in its own quiet way, more unsettling than that. Most of us grow up thinking we know the moon. We know its face, or at least the half it shows us. We know the broad, dark plains called Maria, those old basaltic lava flows that create the familiar patterns people turn into rabbits, faces, and whatever else their imagination is in the mood for. We know that from Earth, the moon seems dependable. It waxes, wanes, rises, sets, and generally behaves like the most reliable object in the sky after the sun. But that sense of familiarity is a bit misleading, because the moon we know from Earth is only one hemisphere. The other half, the far side, stayed unseen by human eyes until the space age, and when spacecraft finally revealed it, the view was not comforting. It was crowded with craters, short on dark volcanic plains, and strikingly unlike the side we thought we understood. That difference matters because it tells us the moon is not a simple world. It is not a smooth grey ball with some dents in it. It is a record of violent impacts, uneven heating, ancient volcanism, and one very stubborn geological mystery. NASA notes that the lunar crust is much thicker on the far side than on the near side, roughly 60 kilometers on the far side versus about 40 kilometers on the near side. That asymmetry helps explain why the near side has so many broad maria, while the far side does not. On the near side, the crust was thinner, and ancient impacts were more likely to open pathways for lava to flood large basins. On the far side, the thicker crust made that much harder, so instead of great dark plains, you get highlands, ridges, scars, and crater upon crater upon crater, as though the moon kept all of its roughest memories on the side we could not see. It is one of those cases where the scary part is not fantasy. It is geology. The far side looks harsher because it is harsher. NASA describes it as heavily cratered and lacking the prominent maria of the near side. Those craters are not cosmetic. They are evidence of an early solar system that was far more violent than the calm sky above your house might suggest. The moon has little atmosphere, almost no weather, and very little erosion, so impacts remain preserved for immense stretches of time. Where Earth recycles its surface through water, wind, plate tectonics, and life itself, the moon keeps the damage. The far side, especially, reads like a stone archive of bombardment. It is the sort of place that makes you realize how much of Earth's gentleness is not normal for the universe. It is a local luxury. There is also the matter of dryness, which sounds less dramatic until you think about what it means operationally. The moon does contain water in certain forms and locations, especially near permanently shadowed polar regions, but NASA still describes the moon overall as extraordinarily dry, even 100 times drier than the Sahara Desert. That is not just a nice line for a museum wall. It means the lunar surface is a place without the easy chemistry and buffering presence of water that we take for granted on Earth. Dust behaves differently. Temperature swings feel more severe. Resources become precious. Any crew flying around the moon is not circling a watered, softened world. They're passing a body that is dry, old, thermally unforgiving, and chemically sparse. Even when there is water to study, it is limited, patchy, and scientifically complicated, not waiting in neat little bottles with labels on them. Now place humans into that picture. Not robots, not orbiters, people. Artemis II is NASA's first crewed Artemis mission, an approximately 10-day journey around the moon and back, designed in part to prove that the Orion spacecraft and its systems can safely carry astronauts through deep space, around the moon and home again. That alone gives the mission a very different feeling from the robotic exploration we often talk about in calm, tidy terms. Instruments do not get homesick. Cameras do not feel small. Hardware does not wonder what would happen if a system failed at the wrong moment. People do. And because of that, a mission like Artemis II is scientific, yes, but it is also personal in a way that no uncrewed flyby can be. The crew is not merely collecting data, they are living inside the distance that data describes. One of the most quietly intimidating parts of that trip is also one of the easiest to describe. When Orion passes behind the moon, the spacecraft enters a planned communications blackout because the moon itself blocks radio contact with Earth. NASA's Artemis II updates describe this blackout as lasting about 40 minutes during the lunar flyby. That is not a typo, and it is not a bit of dramatic storytelling added for effect. For those minutes, Earth cannot simply chat with the crew as usual. There is no direct line, no easy reassurance, no immediate conversation. You're still being tracked by physics, of course, but emotionally that is not the same thing as hearing another human voice from home. Space has many ways to remind you that far is a real condition and not just a poetic word. Silence is one of the most effective. That blackout is one reason the far side feels so different from the moon of postcards and backyard telescopes. The near side, for all its harshness, still faces Earth. It participates in a relationship. The far side does not. Once you slip behind the moon, Earth is no longer in direct communication, and the moon becomes not just an object outside the window, but an actual barrier. It stands between the crew and the entire planet. Every city, every voice, every ocean, every memory of ordinary life sits on the wrong side of a body of rock. In practical terms, the blackout is planned and expected. In human terms, it is still a moment of separation that Apollo crews knew, Artemis crews know, and future lunar travellers will know as well. It is one thing to understand that intellectually. It is another thing entirely to feel it with your own ears. And that is where the word terrifying begins to earn its place, though perhaps not in the way a movie trailer would suggest. The far side is terrifying because it strips away the illusion that exploration is just sightseeing with better cameras. It is older terrain over a colder interior history, a thicker crust, fewer maria, harsher topography, impact history written in plain view, and a communications geometry that briefly takes Earth out of the conversation. It is operationally hostile in the calm, factual way that space tends to be. Nothing is angry, nothing is chasing you. But a world does not need bad intentions to be dangerous. Vacuum does the job very efficiently without ever raising its voice. There is another detail that adds to this feeling, and it is one I find oddly powerful. Cameras are wonderful. Modern spacecraft carry excellent imaging systems, and NASA has already released far-side photos from Artemis II's flyby, showing terrain in ways no earlier generation could casually share with millions of people. But trained astronauts still see things cameras do not see in the same way. NASA emphasized that the lighting conditions during the flyby, with long shadows across the surface, would help reveal depth, ridges, slopes, and crater rims that are harder to detect under full illumination. Human eyes and human judgment matter here. A crew member looking out a window is not merely a passenger beside the instruments. They are part of the observing system, bringing pattern recognition, context, comparison, and emotional response into the act of exploration. That difference between what is recorded and what is experienced became especially interesting when Artemis II astronauts observed impact flashes on the Moon during the flyby. NASA's impact flash work explains that these brief flashes are easiest to see on the shadowed portion of the Moon, where the contrast helps tiny bursts of light stand out. Recent reporting on Artemis II described astronauts visually witnessing multiple meteoroid impacts on the far side, flashes so quick and delicate that human observation mattered in a way static expectation did not fully anticipate. That is a remarkable thing to think about. You travel to the far side of the Moon and, in the darkness, the surface quietly reminds you that it is still being struck. The story of impact is not only ancient history written in craters, it is ongoing. The Moon is still taking hits. This matters scientifically because impact flashes help researchers understand present-day meteoroid activity and the hazards such impacts pose to future missions and infrastructure. But it matters emotionally too because there is something very sobering about seeing an airless world behave like a target range for the solar system. On Earth, many smaller incoming objects burn up in the atmosphere. That protective blanket is so normal to us that we rarely stop to appreciate how much work it does. The Moon does not have that shield, so impacts reach the ground, carve new marks, and occasionally flare with visible light. When you see that from nearby, the lesson is not subtle. Earth is not merely home. It is a sheltered environment, and shelter is easy to underestimate until you spend time around places that do without it. The farther you follow this line of thinking, the more the mission becomes about perspective rather than just procedure. One of the great themes of lunar flight has always been that astronauts leave to learn about another world and return having learned something devastatingly clear about this one. Earth from lunar distance does not look like a map or a set of national boundaries, or a collection of arguments on the internet. It looks singular, small, bright, limited, and strangely delicate. Artemis II's flight around the Moon is technologically ambitious, but the deeper value may be what happens to the people who make that trip. They do not just bring back measurements, they bring back a corrected sense of scale, and scale can be an emotional shock. That shock is not always dramatic in the outward sense. Sometimes it looks like awe, sometimes it looks like grief, sometimes it looks like humility. Astronauts are trained professionals, but they're still human beings with memories, families, fears, and their own ways of processing what they see. A mission can be planned to the second and still contain moments that refuse to stay inside procedure. Looking at Earth from beyond the Moon does that to people. The Moon, especially its far side, sharpens the contrast. One world is dry, pitted, airless, and silent. The other is blue, active, clouded, wet, and full of voices. One preserved the record of bombardment because it lacks erosion and weather. The other softens its scars and keeps making room for life. You do not need a grand speech to feel that difference. The window will do. There is also a psychological weight in knowing that even the most advanced mission is still relying on careful margins. A lunar flyby is elegant, but it is not casual. The spacecraft, trajectory, communications, navigation, life support, and crew workload all have to function together in an environment that does not forgive improvisation for long. The public often sees the polished version of exploration. The launch, the beautiful images, the recovered capsule. The lived version includes checklists, timing, contingency planning, and the awareness that a great deal of very expensive engineering exists because space is actively unhelpful. The far side of the Moon concentrates that feeling. It is the point in the trip where the scenery gets rougher, the signal goes quiet, and the mission becomes more than a line on an animation. And yet, none of this makes the mission bleak. Quite the opposite. The danger is part of why it matters. If the far side of the Moon was simple, smooth, familiar, and easy to explain, it would still be interesting, but it would not press on the human mind in quite the same way. What gives Artemis II its real force is the combination of hard science and human vulnerability. The Moon's two hemispheres are genuinely different. The far side's crust really is thicker, its maria really are sparse, its craters really are dense. The blackout really does happen. The dryness is real, the observational challenge is real, and inside all that reality are 4 people trying to do their jobs, while also being the sort of creatures who can look out at Earth and feel their entire sense of home shift by a few degrees. Sometimes a few degrees is enough to change a life. So when we say what we found on the far side of the Moon is terrifying, the point is not that astronauts discovered monsters or secret machines or anything else the internet would be delighted to misinterpret. The far side is terrifying in a more grounded way. It shows us an older and more battered Moon. It gives us silence when we most want connection. It reminds us that cameras are useful but not complete, that people still matter in exploration, and that there are kinds of seeing that require a human nervous system present in the moment. Most of all, it turns Earth into an answer to a question many of us do not realise we're asking. What makes our world special? A trip around the far side of the Moon gives a very direct reply. This fragile, noisy, wet, warm planet does. And before we move any farther, it helps to sit with one simple fact. The Moon is not one story told twice. It is a world with 2 very different faces, and the hidden one forces us to give up the comfortable idea that what we see from home is the whole truth. The first thing to understand is that the far side of the Moon is not hidden because it is sneaky, cursed, or permanently dark. It is hidden because of motion, timing, and the very steady mechanics of orbit. The Moon is tidally locked to Earth, which means it rotates on its axis in the same amount of time it takes to orbit our planet. As a result, the same hemisphere generally faces us. NASA's Moon Guide explains that this is why only the near side is visible from Earth, while the far side remains out of direct view. It is also why so many people grow up assuming the Moon is visually simple. We keep seeing the same familiar face, so our brains quietly decide the rest must be more or less similar. It is a reasonable guess, and in this case, a very wrong one. That said, the Moon is not perfectly frozen in place from our point of view. It wobbles a little in a motion called libration, and that wobble lets careful observers on Earth see slightly more than half of the lunar surface over time. NASA notes that experienced observers can see about 59% of the Moon's surface thanks to libration. That sounds generous until you realise what it still leaves out. 41% of the Moon stays beyond direct Earthbound viewing. More importantly, even the extra slivers revealed by libration do not amount to a genuine experience of the far side as a world with its own geography, its own large-scale structure, and its own personality. Seeing a little around the edges is not the same as seeing the place. It is more like catching the sleeve of a person and pretending you know their face. There is another misconception worth clearing away before we go further. The far side is often called the dark side, but that phrase is misleading. It does not stay dark. The far side receives sunlight just as the near side does. Day and night sweep across it according to the same lunar cycle. What makes it far is not lighting, it is orientation. It faces away from Earth, not away from the Sun. That may sound like a small correction, but it changes the emotional shape of the story. The far side is not a place the Sun forgot. It is a place we forgot, mostly because for the overwhelming majority of human history, we had no practical way to look at it directly. We had to imagine it, and imagination is often very confident when information is scarce. For thousands of years, every human culture that looked up at the Moon was doing so with only half the object available. That is a remarkable fact when you stop and sit with it. We mapped lunar seas that are not seas. We named craters, bays, and mountains. We watched phases, wrote myths, kept calendars, and composed poems. We made the Moon part of religion, agriculture, navigation, romance, and bedtime. And throughout all of that, the unseen hemisphere stayed unseen, not blurry, not distant in the way Neptune is distant, hidden by geometry. An enormous nearby world was in the sky all the time, and we did not know what half of it looked like. Humans are not especially comfortable with that kind of gap. We like the feeling that if something is close, it should also be knowable. The moon did not cooperate. That began to change in 1959, when the Soviet Luna 3 spacecraft returned the first images of the lunar far side. NASA's historical resources note that Luna 3 took the first picture after passing the moon and looking back at the sunlit far side, and that the mission returned 29 photographs covering about 70% of the far side. Those pictures were noisy and low in resolution, but they were enough to overturn a quiet assumption. The far side did not resemble the near side in any simple way. It was rougher, brighter in broad appearance, more crowded with craters. The familiar dark maria were largely missing. Humanity's first look at the hidden half of the moon did not produce a feeling of symmetry. It produced a feeling of mismatch. And low-resolution surprise is still surprise. Even grainy first looks can rearrange the mind. Imagine having lived in a world where the moon feels as familiar as a relative, then discovering that the face you know is only part of the story, and perhaps not even the more revealing part. It is a bit like learning that the side of a house you pass every day is the polished front, while the back is all service stairs, storm damage, utility lines, and old repairs. Same structure, very different feeling. That is what the far side did to the moon's image in the human mind. It turned a companion into a more complicated object. It also introduced a scientific puzzle that has never entirely gone away. Why are the two hemispheres so different? Over time, spacecraft from several nations mapped the far side in increasing detail. NASA's Lunar Reconnaissance Orbiter and earlier missions transformed the far side from rumour into topography, chemistry, and high-resolution imagery. So in one sense, it would be wrong to say humanity has not seen the far side. We have. We have mapped it. We have measured it. We have rendered it in exquisite detail. Modern imagery can show ridges, basins, crater walls, and subtle changes in terrain with astonishing precision. But the title of this section is not about whether the far side has ever been seen. It is about whether humanity rarely truly sees it. And I think that answer is still yes, because maps and presence are not the same thing, and data does not automatically become felt understanding. Most people do not carry the far side in their heads the way they carry the near side. Ask someone to picture the moon, and they usually imagine the visible maria, the familiar face, the broad patterns visible with the naked eye. Very few can mentally summon the great battered highlands of the hidden hemisphere, or point out the major far-side basins with any confidence. That is not a failure. It is just how familiarity works. The near side is part of ordinary life. The far side is part of scientific literacy only if you have gone out of your way to learn it. So even in the age of global networks and high-resolution maps, the far side remains something humanity knows better on paper than in instinct. We possess the information, but we do not live with it. That gap becomes even more obvious when you look at how rarely humans themselves have been there to look with their own eyes. Before Artemis II, only Apollo crews travelling around the moon ever directly viewed the far side in person. NASA's Apollo 8 materials describe the first crew reaching the far side of the moon and firing the engine burn that made them the first human satellite of another world. Apollo 13's reconstructed far-side views and other mission records remind us that astronauts did indeed see that hidden hemisphere pass beneath them. But the number of humans who have done this is tiny compared with the number of humans who have stared at the near side from Earth. The imbalance is almost absurd. Billions know one face, only a handful have met the other. Even those Apollo glimpses, important as they were, happened under conditions that were hardly leisurely. Lunar missions are busy. Crews are working, reading procedures, managing navigation, monitoring systems, speaking when communication exists, and continuing to function in a place where one mistake can grow teeth. The romance comes later, usually in documentaries. In the spacecraft, there is a schedule. So when we speak of truly seeing the far side, part of the problem is that the people closest to it are often also the busiest people in the room. Their view is real, but it is threaded through task load, mission discipline, and the practical urgency of flight. Space does not usually pause so that a human can gather their thoughts and just have a good long stare. That is one reason Artemis II matters so much. NASA says the mission's 7-hour flyby of the lunar far side returned the first official flyby images captured by the Artemis II astronauts, and included regions no human had seen. NASA also highlighted that the lighting conditions during the flyby would produce long shadows that enhance relief and make ridges, slopes, and crater rims easier to perceive. This is important because the far side is not only rarely seen by humans, it is rarely seen in the kind of light that helps terrain feel physically legible. Flat lighting can make a rugged world look strangely tame. Long shadows restore the shape of danger. They let craters feel like cavities rather than circles, and escarpments feel like drops rather than lines on a screen. There is a practical lesson hidden in that, and it has to do with the limits of cameras. We often assume that a camera sees more objectively than a person. In some ways, that is true. Cameras are precise. They can be calibrated, stabilized, filtered, compared, archived, and reanalyzed. But cameras also flatten experience. They reduce a three-dimensional, shifting, context-rich scene into a frame. A trained astronaut looking through a window brings something else. Motion, depth cues, expectation, surprise, and attention directed by knowledge. That does not make the astronaut better than the instrument in every sense, but it does mean that human observation remains scientifically valuable and emotionally unique. Seeing the far side in person is not just a sentimental bonus for the public relations team, it is its own form of encounter. Then there is the Earth itself, or rather the absence of it. On the near side of the Moon, depending on where you stand, Earth can hang in the sky. On the far side, Earth is hidden below the horizon because that hemisphere faces away from us. Recent NASA Earth Observatory coverage of Artemis II showed Earth set from the lunar far side, a phrase that is beautiful and slightly unsettling for the same reason. It captures the fact that from the far side, home is not overhead. Home is gone. Imagine that for a moment, not as a line in a script, but as a condition of perception. The planet that contains every familiar thing is simply not in sight. The Moon is no longer a stepping stone with Earth always nearby in the window. It becomes a wall that can physically remove your planet from view. That visual loss matters more than people sometimes expect. Human beings orient themselves emotionally with reference points. We do it on roads, in houses, in cities, and in relationships. Even when we do not consciously think about it, we like knowing where home is. The far side takes that comfort and sets it aside. You can know intellectually that Earth is right there on the other side of the Moon, and still feel the difference between knowing and seeing. Knowing is abstract. Seeing is regulatory. Seeing calms the animal part of the mind. Remove the view, add the communications blackout, and the far side begins to feel less like a scenic loop and more like what it really is. A region of space where human beings are temporarily beyond ordinary contact with everything familiar. This is also why the phrase, "humanity rarely truly sees," is not just about optics, it is about relationship. We see the near side in the casual way we see something that belongs to our routine. We see the far side only through effort, machinery, risk, and unusual perspective. One side joins our evenings, the other requires a mission architecture. One side can be admired while carrying groceries from the car. The other demands launch windows, tracking networks, guidance systems, radiation shielding, and a crew willing to leave the basic safety of low Earth orbit. Those are very different levels of access, and they produce very different kinds of familiarity. What makes this especially interesting is that the Moon is still so close by cosmic standards. The far side is not the surface of some exoplanet around a distant star. It is the back half of our own moon. It is a short sentence away in astronomical terms and a long way away in human terms. That contrast reveals something slightly embarrassing about our species. Proximity is not enough. A thing can be close and still remain psychologically remote for centuries. The far side proves that. It also suggests that exploration is not just the acquisition of images. It is the slow work of turning remote facts into lived understanding. A good example is the very phrase, the far side. It sounds simple, almost modest. Yet hidden inside it is a whole package of realities. No direct line of sight to Earth, no direct radio contact during certain flight phases, no familiar lunar face, no broad dark Maria to orient the eye, and a landscape whose crowded cratering makes it visually busier and harder for a non-specialist to read. The near side offers shapes the human brain learned young. The far side offers complexity without the comfort of recognition. That may be one reason it feels more hostile on first encounter. People tend to relax around patterns they recognize. The far side is not in the business of helping with that. And the more carefully you look, the more you realize that our own language gives away the asymmetry. We speak of the moon in ordinary life, but we mean the near side almost all the time. The far side remains a qualified object, as if it is a subsection rather than half the world. That habit shapes public imagination. It keeps the hidden hemisphere in a kind of permanent footnote status, scientifically important but emotionally secondary. Artemis II pushes against that. By carrying humans around the far side and returning imagery, observations and experience from the flyby, the mission reintroduces that hemisphere not as an appendix, but as one of the main places where the moon tells the truth about itself. So when we say humanity rarely truly sees that side of the moon, we're talking about several layers at once. We mean that earthbound viewers almost never see it directly. We mean that even with libration, much of it stays hidden. We mean that the first photographs arrived only in the space age. We mean that only a very small number of humans have ever viewed it firsthand from nearby. We mean that spacecraft images, however excellent, do not automatically create emotional familiarity. And we mean that the far side remains one of those places where scientific access has outpaced ordinary human intuition. We know it better than we used to, and still not in the way we know the moon's face from the yard, the window, or the walk home after dark. Once that point settles in, the next question becomes much sharper. If the far side is rarely seen in the full human sense, then what exactly is humanity missing when it looks only at the near side? How can one small world have two halves that look as if they grew up in different neighbourhoods? The moon is only one body. It formed from the same violent early history, spun through the same solar system, and has been orbiting Earth for billions of years. Yet the hemisphere we know from the sky is darker in broad patches, smoother in major regions, and much more marked by ancient lava plains. The far side, by contrast, is brighter overall, thicker crusted, more heavily cratered, and much poorer in Maria. NASA's own overview of lunar composition puts the problem very plainly. The moon's crust is asymmetrical, thicker on the far side and thinner on the near side. That one sentence carries an enormous amount of consequence. If you want the least dramatic, most useful answer first, here it is. The far side looks so different because the moon did not cool, solidify, and evolve in a perfectly even way. The crust ended up thicker on the hidden hemisphere, thinner on the hemisphere facing Earth, and that difference changed what impacts could do, where lava could rise, how long heat was retained, and what kinds of surface features survived in plain view. In other words, the far side did not become rough and crater-packed, because it was singled out for cruelty by the universe. It became that way because its structure made it less likely to be resurfaced by volcanic flooding. The near side had more chances to cover old wounds. The far side kept them visible. That resurfacing point is important, because people sometimes hear more craters and assume more impacts. But NASA's Lunar Reconnaissance Orbiter work suggests that the difference is not mainly that the far side was hit more often. Rather, the near side shows fewer craters, in part because many were buried or softened by later volcanic lava flows. The far side has a much thicker crust, so even when large impacts punched into it, they were less likely to open pathways deep enough for huge amounts of basaltic lava to pour out and fill the resulting basins. On the near side, thinner crust made that outcome easier. The result is a kind of geological housekeeping imbalance. One hemisphere got a lot more resurfacing. The other lived with the old damage. To understand why the crust ended up so uneven, it helps to go back to the very early moon, when nothing about it was settled. The moon likely formed after a giant impact in the early solar system, and for a long time it would have been far hotter than the grey object we know today. Lunar scientists often describe an early magma ocean, a stage when much of the young moon was molten or nearly so. As that material cooled, different minerals crystallized out at different times. Lighter minerals rose and helped form the crust, denser ones sank lower. That basic process happened everywhere, but the details appear to have become asymmetrical. Something about the moon's cooling and early thermal evolution produced a thicker far-side crust and a thinner near-side crust. Scientists are still working out exactly why. One proposed explanation that has drawn attention for years is the Earthshine idea. In the moon's earliest history, Earth would have been very hot after the impact that formed the moon. Because the young moon was much closer to Earth than it is now, the hemisphere facing Earth may have received extra heat radiated from our planet. NASA astrobiology described a version of this argument by noting that the far side may have been cooler, allowing more crust-forming materials to condense there, while the near side remained warmer longer. Over enough time, that temperature imbalance could help produce a thicker far side crust and a thinner near side crust. It is an elegant idea, partly because it gives Earth a direct role in shaping the split personality of its own moon. The moon did not just orbit Earth. Early on, Earth may have helped cook one side more than the other. Now, to be fair, lunar science is not finished with this story. The Earthshine hypothesis is not the only explanation on the table, and scientists do not treat the mystery as fully solved. There are other factors in play, including the distribution of heat-producing elements, the timing of giant impacts, and the dynamics of how the moon's interior evolved after crust formation. That uncertainty is not a weakness. It is one of the reasons the far side remains so scientifically valuable. When a world keeps a structural asymmetry for billions of years, it is not being difficult for the sake of it. It is preserving a clue. The trick is learning how to read it correctly. One major clue sits on the near side in a region with a name that sounds technical because, regrettably for public relations teams, it is technical. It is called the Procellarum Creep Terrain. NASA's crustal thickness material describes it as a large province on the near side enriched in potassium, rare earth elements, and phosphorus. Those ingredients matter because they are associated with heat-producing radioactive elements. In plain language, the near side appears to contain a concentration of materials that could help keep parts of the crust and upper mantle warmer for longer. A warmer interior is more willing to melt. A more melt-friendly interior is more likely to feed volcanism, and volcanism in turn is how you get those broad dark maria that define the face most of us know. That means the moon's two hemispheres are not merely different at the surface, they appear to differ in deeper thermal history as well. A NASA study published in 2025 reported that the near side is flexing more than the far side under gravitational forces, implying that something about the moon's internal structure is fundamentally different from one hemisphere to the other. The researchers describe this as evidence that the near side and far side did not evolve identically below the surface. That does not instantly solve the whole puzzle, but it does reinforce the broader picture. The far side was not only capped by thicker crust, it likely followed a cooler, less volcanically productive interior path overall. So when people say the far side is colder in its interior history, that is not just a dramatic phrase. It reflects a real scientific effort to understand how heat was distributed inside the moon over time. Once you put these pieces together, the visual difference between the two hemispheres becomes easier to understand. The near side had thinner crust, more internal heating in key regions, and better conditions for large volumes of basaltic lava to reach the surface and flood impact basins. The far side had thicker crust and, overall, less of that later volcanic resurfacing. So ancient basins on the near side often became smooth, dark maria. Ancient basins on the far side tended to remain as cratered highland terrain. Same early solar system, same broad category of impacts, but very different follow-up history. It is a bit like two neighbourhoods hit by the same storm, except one gets decades of resurfacing, repair and repaving, while the other keeps the old breaks in the pavement visible. After long enough, they stop looking like the same event even if they began that way. This also explains why the far side feels harsher to the eye. Cratered highlands are visually busy. They are broken, ridged, pitted, overlapping, and rough in a way that broad lava plains are not. Maria make the near side look calmer, even though they were born from ancient violence. The far side, with its limited maria and crowded highlands, preserves more of the raw impact record in open view. That record is not just messy, it is old. NASA points out that the far side is heavily cratered and lacks the prominent maria of the near side, while the South Pole Aitken Basin on the far side is one of the largest and oldest impact features in the solar system. So the far side does not merely look old, it is old in a very specific geological sense. Large parts of it remain close to the Moon's early history. The South Pole Aitken Basin deserves a brief pause here, because it is one of the far side's great calling cards. NASA describes it as one of the largest and oldest impact features in the solar system, and recent Artemis II imagery emphasized it again as a window into ancient geologic history built up over billions of years. This basin is so large that it is less like an ordinary crater and more like a wound that became part of the Moon's overall anatomy. It matters scientifically because enormous impacts can excavate material from deep below the surface, potentially revealing clues about the Moon's lower crust or even mantle. So when scientists talk excitedly about the far side, they are not being sentimental about hidden scenery. They are talking about access to deep-time evidence that the near side does not preserve in the same way. Another useful way to think about the split is to remember that maria are not just aesthetic features. They are evidence of a world that stayed warm enough in the right places for long enough for internal melts to reach the surface and spread out over huge areas. The near side is rich in these dark lava plains. The far side is not. That absence tells us something about crustal thickness, melt generation, pathways to the surface, and the Moon's thermal budget over time. In a quiet way, the far side's refusal to become a patchwork of maria is one of its most informative qualities. By not being resurfaced as much, it stayed closer to its earlier state. That makes it rougher to look at and more useful to study. The Moon, in this sense, rewarded geologists by refusing to tidy up evenly. There is a practical side to this for Artemis II as well. The crew is not landing on the far side, but flying around it means directly observing a hemisphere whose terrain expresses all of this asymmetry in plain view. Long shadows can sharpen relief, and what the astronauts see is not just more craters. It is the visible consequence of billions of years of unequal crustal thickness, unequal volcanic resurfacing, and unequal thermal history. The Moon's two faces are teaching tools if you know how to read them. One says, here is where lava covered the past. The other says, here is where the past stayed exposed. For a human crew, seeing that contrast directly matters, because it turns geological abstraction into immediate landscape. And yet, for all this progress, the Moon still refuses to hand over a neat, single-cause explanation. Was the decisive factor early Earth heating one side more than the other? Was it the later concentration of heat-producing elements on the near side? Did giant impacts reshape crustal thickness in a way that changed where volcanism could happen? Did more than one of these processes stack together? The answer may well be some combination. Planetary bodies are under no obligation to be simple. and the Moon is not. The reason scientists keep coming back to it is not that it is easy. It is that it is close enough to study in detail, while still being old enough to preserve some of the solar system's earliest chapters. The far side is difficult in exactly the way a good archive is difficult. The pages are all there, but some are burned, some are buried, and some are written in a language you learn only slowly. There is also something slightly humbling about how long it took us to fully appreciate this asymmetry. We had myths about the Moon long before we had topographic maps. We saw the near sides Maria for centuries before understanding that they were ancient volcanic plains. We assumed, naturally enough, that the unseen half would be broadly similar. Only after spacecraft, sample analysis, orbital measurements, gravity mapping, and decades of planetary science did the deeper picture come into focus. Even now, the Moon remains a place where looking and understanding are separated by a long stretch of work. That is worth remembering whenever anyone speaks as if the Moon is a finished subject. It is not finished. It is just nearby. Nearby is not the same as simple. What all of this adds up to is a far side that is not just visually different, but historically different in the sense that matters most to geology. It kept more of its oldest surface expression. It built a thicker crust. It saw less large-scale volcanic flooding. It likely ran cooler in important parts of its interior history. It preserved giant impact structures whose age and scale make them uniquely valuable. And because of that, it gives us a less edited version of the Moon. The near side is a story that has been revised by lava. The far side is closer to a first draft, though draft may be too gentle a word for a place so heavily worked over by impact after impact. From a human point of view, that makes the far side feel more severe. From a scientific point of view, it makes it more honest. You're looking at a surface that shows more of what happened instead of more of what was later covered up. That is one reason the hidden hemisphere seems both puzzling and hostile at once. Its appearance is not a coincidence. It is the visible result of deep structural differences inside the Moon itself. The face we know is not the standard model. It is the more volcanically rewritten half. The far side is what happens when the rewrite is much more limited. Seen from a distance, the far side can look like nothing more than a rougher grey disk. But as soon as you start reading the terrain properly, it stops looking rough in a casual way and starts looking old in a very specific, almost uncomfortable way. The far side is not simply covered in craters. It is dominated by the Moon's highlands, those lighter-coloured regions that preserve the earliest crust. NASA explains that the highlands are dominated by anorthosite and represent the Moon's oldest rocks, more than 4 billion years old. That is a useful number to keep in mind, because it means much of what you are seeing on the far side is not late decoration. It is ancient lunar structure, battered and exposed, surviving from a time when the solar system was a much less polite place. That age shows up in the simplest way planetary geologists know how to read a surface: crater density. Older surfaces generally accumulate more impacts because they have been sitting out longer, with fewer processes to erase the damage. On Earth, age can be hidden by rain, rivers, glaciers, plate tectonics, forests, cities, or the general human habit of paving over anything inconvenient. The Moon does not offer that kind of cleanup. NASA's crater materials emphasize that lunar craters remain unusually well preserved, because the Moon has little atmosphere and very limited erosion. Even a child-friendly NASA explanation makes the same point rather bluntly. The Moon has almost no erosion because it has no atmosphere, no wind, no weather, and no plants. Once a mark is made, it tends to stay. The far side is what happens when a very old surface stays legible for an exceptionally long time. So when the far side looks violently scarred, that is not a dramatic exaggeration. It is exactly what a mostly unhealed impact record should look like. Craters overlap older craters. Smaller impacts pepper the floors and rims of larger basins. Ejecta blankets spread outward. Central peaks rise where the crust rebounded after impact. Some crater walls slump into terraces, Others cut through older structures and create a layered history that has to be untangled feature by feature. What makes the far side feel intense is not only the number of scars, but the way they sit shoulder to shoulder with so little empty calm between them. NASA's educational guide on the moon puts it nicely and accurately. On the far side, many craters stand shoulder to shoulder, chronicling the moon's early bombardment. That is not scenery in the decorative sense. It is a record of repeated collision. There is also a compositional reason the far side feels hard. The highlands are rich in anorthosite, a bright, plagioclast-rich rock linked to the moon's earliest crust. That makes highland terrain look brighter than Maria, but brightness here should not be mistaken for softness or friendliness. It is old crust, fractured again and again by impacts, reduced in places to broken rock, breccia and regolith. The far side's brightness is not a sign of freshness in the everyday sense. It is a sign that large areas were never buried beneath those darker basaltic lava plains that softened the look of the near side. The near side often feels calmer because lava covered and darkened wide basins. The far side often feels harsher because more of the older crust remains exposed, reflecting light and preserving the architecture of damage. If you could hover low over that landscape, the impression would likely be less grey desert and more broken stone country on a scale the eye struggles to organise. NASA's farside imagery routinely shows rugged highland terrain, steep crater walls, rocky ejecta, and surface textures shaped by repeated impact and re-impact. Even a small image description of the farside northern highlands uses words like rugged, which is one of those restrained scientific adjectives that secretly covers a lot of ground. Rugged on the moon can mean sharp relief, scattered boulders, shattered bedrock, blocky slopes, and no atmosphere to soften the view. It also means that shadows matter enormously. Under low-angle sunlight, every rim and drop becomes clearer. Under flatter lighting, the terrain can hide its severity until you look more carefully. That helps explain why astronauts and mission planners care so much about lighting conditions. On Artemis II, NASA noted that the partially illuminated far side would create long shadows across the surface, enhancing relief and revealing depth, ridges, slopes, and crater rims that are harder to detect under full illumination. That is not just a bonus for photography. It changes how the terrain is perceived. Long shadows make the far side look less like a map and more like a place with real verticality. A crater stops being a neat circle and starts looking like a hole. A basin stops being a coloured patch and starts feeling like a structural wound. The far side becomes more physically readable, and with that readability comes a sharper sense of how battered it really is. One of the best examples is the South Pole Aitken Basin, which is not merely another crater but one of the largest and oldest recognised impact basins in the solar system. NASA describes it as a giant far-side structure, roughly 2,500 kilometres across, and recent Artemis II imagery highlighted its eastern edge as part of the crew's observations. This is the sort of feature that changes your idea of what impact damage can even mean. A small crater is a puncture. A basin like South Pole Aitken is more like a reorganisation of the moon's anatomy. It reaches so deep into lunar history that scientists treat it as a key site for understanding the earliest phases of bombardment and the deep materials exposed by ancient impact. On the far side, the scale of injury becomes part of the geology, and South Pole Aitken is hardly alone. Artemis II updates also referenced Hertzsprung, a nearly 400-mile-wide far-side crater northwest of Orientale, as a scientifically interesting region with a distinctive ancient history. Again, what matters is not just the existence of a large crater, but what that crater represents. Repeated large impacts on a hemisphere that did comparatively little to hide them afterward. This is why the far side feels older than the near side, even when both have ancient terrain. Age is not just about the clock. It is about what remains visible. A surface that keeps more of its old basins in open view will feel more ancient because, in practical visual terms, it is offering fewer later edits. Now, when we call the far side harder, we're not only talking about emotional texture, we're talking about the physical consequences of an airless, water-poor impact process surface. On Earth, rock can be rounded by streams, weakened by chemical weathering, penetrated by roots, expanded by freezing water, or buried beneath sediment. On the Moon, especially in the highlands, mechanical destruction comes mainly from impacts and thermal stress rather than weather in the earthly sense. The result is a surface that is both shattered and persistent. It breaks, but it does not wash away. It powders into regolith, but the regolith itself is made from countless acts of violence. Lunar soil is not mellow beach sand. It is more like the dust of repeated impacts, a mixture of broken mineral grains, glassy fragments, melt products, and tiny jagged particles shaped by a world without atmosphere. That top layer is constantly being reworked by what scientists sometimes call impact gardening. NASA's visualization materials explain that impacts mix and disturb the top layers of lunar regolith, spraying excavated material outward and churning the surface over time. It is a cheerful phrase for a process that is not especially cheerful if you happen to be standing there. The far side is old, but it is not inactive in the sense of being untouched. Micrometeorites and larger impacts continue to disturb the surface. So the violence recorded there is not only historical, it is ongoing, just usually on smaller scales than the giant basin-forming events of the early solar system. This is one reason the Moon remains a useful laboratory for impact science. It is still participating. That ongoing activity became especially vivid during Artemis II, when astronauts visually observed impact flashes on the lunar far side. NASA's Impact Flash Project notes that these flashes are easiest to see on the shadowed part of the Moon, and that they help scientists learn about meteoroid impacts and hazards. There is something unnerving about knowing the Moon is still being struck often enough that a nearby crew can watch it happen, not because the Moon is unusually unlucky, but because it lacks the atmospheric shield Earth enjoys. Here, many smaller incoming objects burn away above our heads and never reach the ground. On the Moon, they hit. On the far side, against darkness, some of them briefly announce themselves with light. A violently scarred landscape is not merely the result of what happened long ago. It is also the kind of place where the process has never fully stopped. Another reason the far side looks so severe is the relative lack of visual rest. The near side has Maria, those broad dark planes that create large coherent shapes the eye can hold on to. The far side offers fewer of those calmer expanses. Instead, the view is dominated by highlands and overlapping craters, so the brain has to work harder to organise what it sees. This matters more than it may sound. Human perception likes big patterns. We relax when there are broad regions to group together. We feel more tension when the scene is fragmented, repetitive, and topographically crowded. The far side is all of that. It is not simply geologically rough, it is visually demanding. Looking at it for long enough gives the odd impression that the Moon spent billions of years being hit, and almost none of those impacts were considerate enough to line up neatly. There is a small but important difference too between being old and being hard to read. The far side is both. Some regions preserve ancient crust directly. Some preserve gigantic impact features from deep time. Some have been overprinted by later craters so many times that the landscape becomes a kind of palimpsest, one event scribbled over another. For scientists, this is thrilling and occasionally annoying, which is often the best combination. A simple surface can be easy to classify, but it rarely yields as much history. A complicated surface demands more work, yet often gives more information. The far side is full of places where every rim, terrace, ejecta, blanket, and superposed crater carries timing information if you know how to compare one feature against another. It is like reading a very old legal document that has been stamped folded, watermarked, and annotated by generations of clerks. Messy, yes, but very informative. Age also affects the far side emotionally, because old surfaces imply survival through immense spans of time. The highlands are leftovers from the moon's earliest crust. Many of the Great Basin structures date back to the solar system's most intense bombardment periods. To look at the far side, then, is to look at terrain that has endured through almost the entire history of the Earth-Moon system. It existed while Earth was still a very different planet. It was there before oceans look the way they do now, before multicellular life, before forests, before mammals, before us. That does not make the far side alive or mystical. It just makes it profoundly old. An extreme age has a way of feeling eerie when it is preserved this clearly in the open. It is also worth remembering that older in planetary geology often means more exposed to punishment. A younger surface on the moon might be younger because lava resurfaced it, or because some newer process erased older markings. An older surface is one that has stayed out under the cosmic weather, if we can borrow that term from a place with no weather at all. The far side's highlands have been sitting there, collecting impacts, being chipped into regolith, absorbing temperature swings, and preserving the evidence. So old age and violent scarring go together naturally. The longer the archive remains open, the more entries it receives. That is one reason crater counting works. Time and damage accumulate together. From the standpoint of human exploration, this creates a double impression. Scientifically, the far side is precious because it preserves history. Operationally, it is intimidating because preserved history often means preserved roughness. A smoother basaltic plain is easier to imagine landing near, driving across and mapping in broad strokes. A heavily cratered highland surface is less forgiving to the eye, and potentially less forgiving to machinery. Artemis II is not landing there, of course, but flying over such terrain while communication drops out behind the moon sharpens the psychological contrast. The hidden hemisphere is not only unseen, it is also physically severe in the ways that matter to explorers. Topography, impact record, surface disruption, and a sense that the place has not been made easy for visitors. Still, it would be a mistake to imagine the far side as uniform chaos. Even violent surfaces have structure. There are giant basins, younger craters cut into older terrain, bright ray systems, highland plains, local patches of mare material, and subtle clues about crustal thickness and composition. Some far-side craters are relatively young and sharp-edged. Others are ancient and softened by later impacts. Some central peaks expose material from depth. Some ejecta patterns reveal directionality and impact dynamics. This is not random damage scattered by chance. It is a system of scars with hierarchy, timing, and physics behind it. That is why planetary scientists can look at a battered lunar landscape and feel excitement rather than despair. To them, every scar is a measurement waiting to be interpreted. For the rest of us, though, there is no harm in admitting that the far side feels a little brutal. Not evil, not haunted, just brutally honest about what an unprotected world looks like after billions of years in a crowded solar system. It is the kind of place that makes Earth's forests, rivers, and atmosphere seem less ordinary than they did 5 minutes earlier. A landscape older than 4 billion years, with little erosion, ongoing impact gardening, giant basins, shoulder-to-shoulder craters, and exposed highland crust is not merely geologically interesting. It is a reminder that gentle is not the default setting for rocky worlds. And once that impression sinks in, another question naturally follows. If the far side is so dominated by old highlands and impact scars, where are the familiar dark plains that soften the near side? Why does the moon's hidden hemisphere have so few Maria compared with the face we know so well? That missing darkness is one of the strangest things about the far side once you know how to look for it. On the near side, the moon presents broad, dark plains so obvious that people noticed them long before telescopes became powerful enough to do much about them. Those plains were named Maria, Latin for seas, because early observers thought they might actually be bodies of water. We now know they are nothing of the sort. NASA explains that Maria are large, flat plains of solidified basaltic lava, created when ancient impacts formed basins and later volcanic eruptions flooded them with dark, iron-rich rock. So when you look at the near side and see those familiar dark patches, you're not just seeing surface colour, you're seeing the remains of a major volcanic chapter in lunar history. The far side, by contrast, looks as though that chapter was cut short or at least heavily edited down. NASA's historical summaries note that one of the first big surprises from early far-side images was the striking absence of the large, dark, smooth mare plains that cover about a third of the near side. Even modern overviews keep returning to the same blunt point. The far side has fewer of the smooth, dark Maria and many more craters. This is one of the most visually obvious clues that the Moon did not evolve evenly. You do not need a chemistry lab to notice it. The hidden hemisphere simply lacks most of the features that make the near side feel familiar. It is like finding out that the back half of a house has almost none of the paint, paving or remodelling visible from the street. And the Maria matter because they are not decorative surface stains. They are geological evidence of a very specific sequence. First, a large impact forms a basin. Then, sometime later, molten rock from the Moon's interior rises through cracks and weaknesses in the crust. That lava spreads, cools and hardens into dark basaltic plains. NASA's moon formation material says this directly. Lava flowed up through cracks in the Moon's crust and filled impact basins. So if Maria are largely missing from the far side, the question is not just, why is it lighter? The deeper question is, why did so many ancient basins on one hemisphere get flooded with basalt, while comparable structures on the other hemisphere did not? That is where the Moon's uneven history becomes impossible to ignore. Part of the answer is structural. NASA's composition page describes a major difference in crustal thickness, about 60 kilometers on the far side and about 40 kilometers on the near side. A thinner crust is easier for magma to penetrate. A thicker crust is harder to break through. So even if both hemispheres experienced major impacts, the near side had a better chance of turning some of those impact basins into Maria, because lava had more pathways to the surface. The far side, with its thicker crust, was much less willing to cooperate. It is a bit like trying to push liquid through two lids, one thin and one thick. The thinner one gives way more often. The thicker one keeps more of the molten material trapped below. But crust thickness is not the whole story. There is also the matter of heat, and heat in planetary geology is really another way of talking about opportunity. The near side appears to have had more of the heat-producing ingredients needed to keep parts of the crust and mantle active for longer. NASA's materials on lunar crustal thickness point to the Procelarum creep terrain, a near-side province enriched in potassium, rare earth elements, and phosphorus. Those are associated with radioactive heating, which can help maintain temperatures that encourage melting. More heat means more chance for magma generation, and more chance for volcanism. Less heat means less of both. So when we say the Moon's history was uneven, we mean not only that the crust was thicker on one side, but that the internal energy budget was unevenly distributed as well. That combination, thinner crust plus more internal heating, gave the near side a geological advantage in becoming dark and smooth in large places. The far side did not enjoy that same advantage. So what we see today is not merely a coincidence of colour, it is a record of which hemisphere had the better conditions for large-scale volcanic resurfacing. The near side became the place where great basins were repeatedly transformed by lava. The far side remained, for the most part, a place where the basins stayed visible as basins, and the highlands stayed in charge of the overall look. If the near side is a world that was repeatedly revised, the far side is closer to a draft that kept the original damage in view. It is also important not to turn the absence of Maria into an absolute. The far side is not completely mare-free, and that actually makes the story more interesting. NASA image descriptions point out that Mare Moscoviense is the largest mare deposit on the far side, and that Mare Ingeni is one of the few far-side Mare basalt deposits. Tsiolkovsky crater, one of the most striking features on the far side, is also partly filled with Mare basalt. These exceptions prove that the far side was not volcanically dead in some total sense. It did produce basaltic flooding in select places. The real mystery is why those places are so rare and isolated compared with the near side, where Maria are broad, numerous, and central to the Moon's familiar appearance. Those exceptions are scientifically useful because they let researchers compare far-side volcanism with near-side volcanism instead of treating the two hemispheres as all-or-nothing opposites. NASA's description of Mare Moscoviense makes exactly this point. Because far-side basalts are rare, sampling them would provide valuable insight into how the far-side mantle differs from the near-side mantle, and help explain why Mare basalts are so much rarer there. That's a very neat example of how scarcity increases value. The far side's few Maria are not minor curiosities. They are windows into the underlying reasons the two hemispheres diverged. In some ways, the rare places where the far side did flood with basalt are more informative than the places where it did not, because they show the exception operating under different constraints. This is why the phrase, "the missing Maria," is so powerful. It sounds like a simple observational note, but it is actually shorthand for a whole cascade of uneven processes. Crust formed unevenly, heat was distributed unevenly, volcanic activity was sustained unevenly, impact basins were flooded unevenly. Surface resurfacing happened unevenly, and after all that, the Moon ended up looking uneven in a way that even a child can see through binoculars. It is one of those lovely cases in science where the visual clue is obvious, but the explanation behind it takes decades of orbital data, sample analysis, and theoretical work to unpack. The Moon practically points at the puzzle with both hands, then refuses to give the answer away for free. The Maria also remind us that the near side we know so well is not the Moon in its rawest state. It is the Moon after a considerable amount of volcanic revision. That is worth pausing over, because many people intuitively think of the dark plains as original features, almost like pigmentation. They are not. They are later history written over older impact structures. The more basalt flooded a basin, the more it changed the visual and topographic character of that region. Some craters were partly buried, some basin floors became smoother, some large dark patterns emerged that now dominate how humans imagine the Moon. In that sense, the near side is not just the visible side, it is the more edited side. The far side looks stranger partly because it has fewer of those edits. That editing changed not only the look of the Moon but also its feel. Broad Maria give the eye room to rest. They create recognizable dark shapes that human beings have folded into myths, cartoons, calendars, and songs. Without them, the far side feels visually harsher and more crowded. There are fewer large dark plains to simplify the landscape, and more cratered highlands to complicate it. So the missing Maria are part of the reason the far side feels more alien even before you know anything about lunar geology. The near side offers familiar patterns. The far side offers a lot of geology and very little visual sympathy. It is not trying to be readable from your backyard. There is another layer to the Moon's uneven history, and it has to do with time. Maria did not all form at once. NASA notes that Maria are seas of cooled lava that flooded impact basins between roughly 4.2 and 1.2 billion years ago. That means the near side's dark plains represent a long interval during which volcanism remained important. The far side's lack of comparable widespread Maria suggests it missed much of that prolonged resurfacing. In other words, the two hemispheres did not just begin differently. They stayed different as lunar history unfolded. One side kept opening opportunities for lava to reshape the surface. The other side, generally speaking, did not. So the imbalance is not a single moment frozen in stone. It is an imbalance sustained over immense stretches of time. That sustained imbalance is one reason the far side preserves older terrain so effectively. If a basin never fills with large volumes of basalt, its impact structure remains visible for later craters to overlap, disturb, and complicate. If a basin does flood with basalt, much of that earlier structural detail can be buried or softened. The result is that the near side often shows younger volcanic surfaces superimposed on ancient impact architecture, while the far side more often leaves the impact architecture in plain sight. You could say the near side gives us a moon that kept rebuilding parts of itself, while the far side gives us a moon that mostly endured what happened and carried on looking battered. It is a less flattering face, but perhaps a more revealing one. The rarity of far-side Maria has also become more than an academic curiosity in the era of modern exploration. NASA's 2024 notice about Chang'e 6, for example, highlighted a landing site in the Apollo basin on the lunar far side, a region of huge scientific interest, partly because it offers access to far-side materials tied to this uneven history. Missions like that matter because the far side's few mare deposits are not just visually unusual. They may preserve clues about mantle melting, basin formation, and the limits of far-side volcanism. Every time we look closely at one of those exceptions, we are really asking a big question. Under what circumstances could the far side behave a little more like the near side, and why did it do so only rarely? Another useful detail is that mare basalts themselves tell a story of weight and stress. NASA photojournal notes on lunar grabens explain that tension zones are often found at the margins of mare basalt deposits because those dense lava plains weigh down the crust. That means Maria are not only evidence of past eruptions, they also alter the moon mechanically after they form. They load the crust, help create wrinkle ridges and related structures, and become part of later geological evolution. So when the far side lacks Maria, it is also missing some of the secondary effects that come with those dense basalt plains. The uneven history does not stop at colour contrast. It extends into how the crust responded to the weight of ancient lava itself. All of this adds a quiet irony to the moon's appearance from Earth. The side we know best is not necessarily the side that best represents the moon's baseline condition. It is the side that happened to undergo especially strong volcanic modification and happened to face us while doing it. The side we cannot see directly from Earth is in some ways closer to the moon's older, more heavily cratered, less volcanically softened reality. So the moon's public face may actually be the more misleading one if what you want is an honest summary of how battered and asymmetrical the body really is. That does not make the near side false, of course, it just makes it selective. Like all good introductions, it leaves a lot out. This is one reason the far side matters so much to Artemis II as a human experience. When astronauts swing around the hidden hemisphere, they are not merely seeing the back. They are seeing the half of the moon where the missing Maria forced the geology into plain view. The contrast between the two hemispheres becomes immediate. One side holds the dark lava plains humanity has known for centuries. The other presents a surface where those broad plains are largely absent, and the older structure is left exposed. It is one thing to understand that from orbital maps or a textbook diagram. It is another to look out the window and see that the familiar moon really does have another face, and that this face is more battered, less revised, and much less eager to look friendly. And then there is the emotional consequence of all this missing darkness. The near side's Maria gave human beings shapes to live with. We turned them into faces, animals, stories, and signs. The far side offers almost none of that visual comfort. It is harder to personify a place that mostly presents craters and highlands. So in a subtle way, the Maria help domesticate the near side in human imagination. Their absence on the far side leaves the hidden hemisphere less myth-friendly and more geologically blunt. That too contributes to the sense that the far side is not just scientifically different, but psychologically colder. One hemisphere became part of culture, the other stayed more like evidence. Still, the missing Maria do not simply tell us that the far side had less volcanism. They tell us the moon's history was uneven from the inside out. Uneven crust, uneven heat, uneven melt production, uneven resurfacing, uneven visual legacy. When people say the far side is older, harsher, stranger, and more puzzling than the near side, This is a big part of what they mean. The absence of those broad, dark basalt plains is not a small missing feature. It is one of the main fingerprints left by billions of years of unequal geological opportunity. The Moon did not become two-faced by accident. It became two-faced because its evolution was lopsided, and the Maria are among the clearest signs of that lopsidedness. If the missing Maria tell us that the far side was less volcanically rewritten, the next question is what kind of moon is left behind when that rewriting does not happen very much? The answer is something close to dry stone under a thick lid, not wet sediment, not a world of easy chemistry, and not a place where heat regularly found its way upward to refresh the surface. NASA's own lunar water materials use a wonderfully blunt comparison. The Moon is about 100 times drier than the Sahara Desert. That line is useful because it corrects a common mistake. When people hear that water has been detected on the Moon, they sometimes picture something more abundant than what is actually there. Lunar water exists in limited forms and environments, but the Moon as a world is still overwhelmingly dry. The far side, with its rugged highlands and limited volcanic plains, presents that dryness without much disguise. That does not mean the Moon is completely waterless. NASA states clearly that water exists in both sunlit and shadowed areas of the lunar surface, and that cold traps near the poles can preserve ice. This is important scientific news, and for future exploration it matters a great deal. But there is a difference between some water exists and this is a damp world. The Moon is still an environment where dryness is the rule, and water is the exception that has to be hunted down, mapped carefully and protected. So when we say dry stone, we are not denying the discoveries of lunar water, we are putting them in scale. The far side, especially when seen during a flyby, rather than at a carefully selected polar resource site, is not a place that feels hydrated in any ordinary earthly sense. It feels mineral, dusty, airless, and spare. That dryness affects how the place looks and how it behaves. Without an atmosphere to redistribute heat, the Moon experiences extreme temperature swings. NASA notes that temperatures near the equator can climb above 250 degrees Fahrenheit in sunlight and plunge below -200 after nightfall, while permanently shadowed polar regions can be colder still. These are surface conditions, not the deep interior, but they help reinforce the basic character of the environment. The Moon does not soften extremes, it keeps them. On the far side, that means a surface that has been repeatedly broken by impacts, baked by sunlight, chilled by long nights, and left exposed without weather, water cycles, or any thick air to moderate the punishment. Dryness here is not a side detail. It is part of the whole operating system. Now move downward, below the dust and crater rims, and the next major fact appears: crust. NASA's composition page puts the asymmetry plainly. The Moon's crust is about 37 miles, or 60 kilometers, thick on the far side and about 25 miles, or 40 kilometers, thick on the near side. That is a huge difference for a world this small. It means the far side has a much heavier lid over whatever was happening beneath it. If you want magma to reach the surface, a thinner lid is helpful. If you want a world to hold on to its early battered appearance, a thicker lid is more cooperative. So the far side's thick crust is not just a structural curiosity. It is one of the main reasons the hidden hemisphere stayed more cratered, less flooded, and more obviously ancient. A thick crust changes the Moon's story in several ways at once. First, it makes it harder for magma to break through and spread across the surface as mere basalt. Second, it helps preserve highland terrain by limiting the resurfacing that would otherwise darken and smooth large basins. Third, it reflects a deeper asymmetry in the Moon's formation and cooling history. A crust does not become that uneven by accident in a simple system. Something about the early Moon caused one hemisphere to build or maintain a thicker outer shell than the other. The fact that scientists still debate the full explanation is not a sign of weakness in lunar science. It is a sign that the Moon preserved a subtle, but very consequential problem for us to solve. The thick crust also helps explain why the far side can feel colder in a geological sense, even when the surface itself may be blistering hot in sunlight. That distinction matters. Colder interior does not mean that astronauts flying over the far side would somehow see frost on every crater wall. It means that, over deep time, the far side appears to have had less internal heat available in the upper crust and mantle for driving extensive volcanism. NASA-supported research on lunar basin formation has argued that the near side crust and upper mantle were hotter than the far side during key parts of basin history, and that this thermal contrast helped produce different impact basin behaviour and different volcanic outcomes. A hotter near side was more capable of large-scale volcanic modification. A cooler far side was more likely to stay rigid and preserve old damage. That interpretation fits very well with newer NASA work showing that the Moon's near side flexes more than its far side. In 2025, NASA reported that spacecraft gravity data revealed a fundamental difference in the internal structure of the two hemispheres. Put more simply, the near side seems to yield a bit more under gravitational forcing, while the far side behaves more stiffly. That does not mean the far side is a frozen brick all the way down, but it does reinforce the idea that the Moon's internal evolution was not balanced. One hemisphere retained or expressed heat differently than the other. So when we call the far side colder, we're talking about a world whose hidden half seems to have run on a leaner thermal budget for much of its history. At the same time, the Moon as a whole is not geologically dead in the way people sometimes imagine. NASA's materials on moonquakes explain that the Moon has been cooling and shrinking over time. As it cools, it contracts, and the brittle crust breaks along thrust faults. NASA estimates that over the last several 100 million years, the Moon's diameter has gotten about 150 feet smaller. That is not the behaviour of a world that still has abundant easy volcanism on the surface, but it is the behaviour of a world whose interior is not simply finished. There is still heat inside, there is still adjustment, there is still stress in the crust. The Moon is old, but old is not the same as inert. NASA's composition materials add another useful detail. The Moon's mantle is mostly solid, but the zone closest to the core is partly molten, and some moonquakes may originate there. That gives us a better picture of the lunar interior. The Moon is not hollow, not uniformly cold, and not static all the way through. It has a layered structure with a crust, mantle, and core, and at depth there are still regions that have not fully given up all their heat. Yet this makes the far side contrast more interesting, not less. Because if the Moon, as a whole, still carries some internal warmth, then the far side's surface history becomes even stronger evidence that warmth alone was not enough. What mattered was where the heat was concentrated, how the crust was built, and whether magma could exploit weaknesses to reach the surface. On those terms, the far side was clearly at a disadvantage. There is a practical image that may help here. Imagine the Moon as a pot that once held a lot of internal heat. The near side had a thinner lid in some places and more of the right ingredients underneath to keep certain regions hot, so some of that internal material had a chance to rise, spill out and spread. The far side had a thicker lid and, broadly speaking, a cooler upper interior history, so it vented far less. The pot was not equally leaky. One side simmered longer and expressed that simmering at the surface. The other side mostly kept its contents down below. That is not a perfect analogy, because the Moon is more complicated than cookware, but it gets at the central point. Surface differences on the Moon are really a story about how efficiently different regions could turn internal conditions into visible geology. This is also where dryness and crustal thickness start to feel connected rather than separate. A thick, far-side crust limited volcanic resurfacing. Less volcanism means fewer broad basalt plains. Fewer broad basalt plains mean more exposed highlands and impact structures. Add an environment that is globally very dry and airless, and you end up with a surface where old rock, shattered crust, and pulverized regolith dominate the visual impression. The far side does not look lush or dynamic, because the geological pathways that could have softened or darkened it at large scale were comparatively restricted. It is the moon's less revised half, and dryness makes that unrevised quality feel even starker. There is an important emotional consequence to this as well. The near side can trick the eye into thinking the moon has broad, calm regions, almost like a world that settled down and made peace with itself. The far side, especially once you understand the thick crust and colder interior history, feels more closed off. It is the side where the lid stayed on, the side where heat did not rewrite the past nearly as much, the side where old structures survived because not enough molten rock came later to cover them. There is nothing supernatural about that, but it does create an odd psychological effect. The far side begins to seem less like another view of the same body, and more like the more difficult half of a biography. Dryness also matters for future operations in a bluntly practical way. Water on the moon is scientifically exciting and strategically important, but it is not distributed the way a traveller from Earth would wish. It tends to favour colder, shadowed, or otherwise special environments. That means any crew passing the far side is not flying over a world with easy natural support. They're flying over a place where resources must be identified carefully, and where most of the visible terrain offers little comfort. The old dream version of lunar exploration sometimes imagined the moon as a quiet desert, where you could just arrive, collect what you need, and get on with the adventure. The more accurate version is that the moon is a precise logistical problem wearing the costume of a grey sphere. And then there is the engineering perspective on thick crust. A thick crust is not merely a historical feature, it affects gravity signatures, basin structure, and what kinds of deep materials can be exposed by impacts. NASA's Gravity Recovery and Interior Laboratory, along with later analyses, helped sharpen the picture of how variable lunar crustal thickness really is. That matters because crustal thickness is a sort of geological gatekeeper. It controls how much of the interior can communicate with the surface. On the far side, that gatekeeper was stricter. As a result, a lot of what we learn from the far side comes not from lava plains, but from giant impacts that punched into the crust and revealed deeper layers. In a strange way, the far side gives up its secrets less through eruption than through injury. That helps explain why the far side is such a compelling scientific target despite, or perhaps because of, its harshness. If the near side tells us about the moon's volcanic maturity, the far side tells us more about crustal survival, thermal asymmetry, and the limits of that volcanism. It shows us what happened where magma mostly did not win. It shows us what a smaller, cooling world looks like when one hemisphere remains more rigid, more elevated in crustal thickness, and less overprinted by lava. The moon's hidden half is not just the side without the famous dark seas, it is the side where the moon's internal differences are hardest to ignore. Even the moon's quakes point quietly in the same direction. NASA's educational material notes that moonquakes are fewer and generally weaker than earthquakes, probably because the moon is smaller and has a cooler interior than Earth. That is true for the moon overall, but it makes the far side story easier to appreciate. We're not dealing with a geologically noisy world. We're dealing with a body that cooled fast enough and thoroughly enough that much of its activity faded long ago. Within that already cooler object, one hemisphere appears to have stayed cooler and more rigid still in the crust and upper mantle. So the far side is, in a sense, the stern version of an already stern world. The human consequence of all this is subtle but powerful. A crew flying around the far side is not just seeing a hidden landscape. They are seeing the exposed result of a long geological imbalance, a dry surface on a world with limited water, a thick crust that resisted resurfacing, and an interior history that seems to have been cooler and less volcanically expressive than the near side. That combination makes the far side feel older, yes, but also more sealed, more withdrawn, less willing to tell its story in the easy language of smooth, dark plains. Instead, it speaks in highlands, preserved scars, and the visible absence of things that happened elsewhere. The far side is informative, partly because so much did not happen there. And once that begins to make sense, the mission itself sharpens again. Because none of this is just an abstract lesson in lunar geology. Artemis II has to carry people around that hidden hemisphere, through a place where the moon becomes both a scientific puzzle and a very real barrier between the crew and Earth. The rock may be old, dry and cold in its interior history, but the human experience of passing it is immediate. And that silence is not metaphorical. It is not the kind of silence people mean when they say a place feels lonely. It is a physical communications event caused by geometry, radio propagation, and a very large body of rock getting directly between a spacecraft and Earth. During Artemis II, NASA described a planned communications blackout lasting about 40 to 41 minutes as Orion passed behind the moon. The lunar surface itself blocks the signals travelling between the spacecraft and Earth through NASA's deep space network. So when the crew crosses onto the far side, the quiet is not poetic exaggeration. It is a scheduled loss of contact built into the mission profile. That is one of the most important facts to sit with, because modern life trains us to assume that communication is ambient. Your phone pings, your watch vibrates, aircraft speak to controllers, cars know where they are. If something goes wrong, somebody somewhere can usually be reached within seconds. Artemis II is a reminder that those habits belong to a protected technological environment near Earth. The far side of the moon does not care about our expectations. When Orion slips behind the moon, there is no direct line of sight to Earth-based antennas, and no line of sight means no routine radio link. Silence, in that moment, is not a malfunction. It is simply what the universe looks like when a sphere of rock blocks the path. NASA has been careful to describe this as planned, expected, and familiar in the context of lunar missions. Similar blackouts occurred during Apollo-era missions and during Artemis I, and NASA notes that they remain an aspect of missions operating on or around the lunar far side when relying on Earth-based communications infrastructure. That is reassuring in one sense. The blackout is not a surprise ambush waiting in the dark. Mission control knows it is coming. The crew knows it is coming. Procedures account for it. But familiarity does not remove weight. A planned silence can still feel very different from an accidental one, yet it remains silence all the same. Humans are good at preparing for an event and still feeling it when it arrives. It helps to understand what the Deep Space Network actually is in practical terms. The DSN is NASA's global system of giant radio antennas used to communicate with spacecraft far from Earth. It is how mission controllers track, command and receive data from spacecraft operating in deep space. As long as a spacecraft has a usable path to Earth, the DSN can listen and talk. But when the moon itself is in the way, that path is cut. Not weakened, cut. The signal does not take a polite detour around the lunar limb and carry on as if nothing happened, at least not in any way suitable for routine direct communication under the current mission setup. The moon becomes, for those minutes, both destination and wall. This is one of the reasons the far side has long been interesting not only for exploration, but also for radio astronomy. NASA has pointed out that the far side is shielded from much of Earth's radio chatter because the moon blocks those signals. In astronomy, that quiet can be a gift. For a spacecraft crew used to mission loops, uplinks, telemetry, and the steady presence of Earth-based support, the same quiet can feel more serious. The far side is radio quiet for the same reason it is operationally isolating. Earth is on the wrong side of the moon. A place that is ideal for listening to the universe is, by the same token, a place where Earth cannot casually keep talking to you. What makes the blackout especially striking on Artemis II is that it happens during a flyby that is already emotionally loaded. NASA described the far side passage as including an Earth set, the moment Earth dropped below the lunar horizon as Orion travelled behind the moon. That detail matters because it lines up the sensory and communications experience. The crew does not just lose radio contact, They also lose the sight of Earth itself, so the event is not merely technical, it is perceptual. Home disappears from the window, and the voices from home disappear from the headset. Even when you know exactly why that is happening, the combination has a force to it. It turns the abstract idea of being far away into something almost bodily immediate. Now, to be clear, blackout does not mean helplessness. Orion does not suddenly become blind, drifting and confused like someone who dropped their keys in a dark parking lot. The spacecraft still has onboard systems, navigation, computers, sensors, timelines, procedures, and a trained crew. The mission is designed with this gap in contact in mind. Critical events are sequenced accordingly, and once Orion re-emerges from behind the moon, NASA expects the network to reacquire the signal quickly and restore communication with mission control. The blackout is serious, but it is not reckless. This is an important distinction. Human exploration is not about charging into silence with fingers crossed. It is about building enough capability into the vehicle and crew that silence can be crossed on purpose. Still, the psychological shift is real. A spacecraft in low Earth orbit has the planet constantly nearby. A spacecraft behind the moon does not. In low orbit, even if the crew is in danger, Earth feels close and involved. During a far-side blackout, the crew is operating without immediate conversation with the people whose voices have anchored the mission from the ground. No one is reading up the next line in real time. No one is answering instantly. No one can hear a change in tone and ask, "Say again?" There are moments in exploration when technology extends us outward while still keeping us emotionally tethered. The blackout is one of the moments when that tether goes slack. That slackness has a very human dimension because space crews do not experience mission control merely as a technical service. Those voices are part of the social structure of the mission. They confirm, guide, steady, and in subtle ways normalize the environment. A calm voice from Earth can make deep space feel less alien. Remove that voice, even temporarily, and the environment changes character. The spacecraft becomes smaller. The soundscape changes. The crew is left with one another, with the machinery, and with the view outside. For some people that might feel peaceful. For others, or for the same person a few minutes later, it might feel weighty. The same silence can soothe and unsettle depending on what the mind does with it. There is also the matter of scale. NASA's Artemis II details note that during the lunar flyby, Orion passes within about 4,070 miles of the lunar surface and reaches a maximum distance of about 252,760 miles from Earth. Numbers like that are easy to glance over, but during blackout they gain emotional texture. Distance stops being a fact and becomes a condition. The spacecraft is not just out there in a general sense. It is farther from Earth than any human mission since Apollo, crossing behind the moon where Earth-based signals cannot reach directly. You can know the mission is under control and still feel the significance of that geography. The crew is not merely visiting a pretty object. They are passing through a zone where Earth's presence has limits. Apollo crews knew this version of lunar silence too, and that continuity matters. NASA's modern Artemis II coverage explicitly notes that these blackouts echo the Apollo missions. This connects Artemis II not just technically but emotionally to the earlier era of lunar exploration. The far side is one of the places where the mythology of spaceflight becomes practical again. You're doing the work, following the timeline, managing the spacecraft, and also experiencing one of the oldest truths of deep space travel. Sometimes the line home goes away for a while. It is a quiet kind of danger, not loud or cinematic, but it reminds everyone involved that distance has consequences beyond fuel and trajectory. In a way, the blackout is a very clean test of what crewed exploration actually means. Robotic spacecraft spend long periods without real-time hand-holding all the time. They execute programmed actions, store data, wait for communication windows, and carry on. People are different, because part of the value of crewed missions is that humans can adapt, notice, judge, and respond in ways machines cannot. but that same adaptability comes with awareness. A crew knows they are temporarily alone in the operational sense. They know that no one on Earth can jump into the loop and fix the moment instantly. That is not usually how assistance works in deep space anyway, but the blackout makes the principle impossible to ignore. It is one of the few moments where the mission's autonomy becomes emotionally visible. What I find especially interesting is that the blackout is both ancient and modern at once. Ancient in the sense that it is caused by simple geometry that Apollo crews also faced. Modern in the sense that Artemis II flies with advanced communications technology, including optical communications work, sophisticated onboard systems, and a much broader network architecture than anything available in the 1960s. Yet even with all that progress, NASA still describes a blackout behind the moon because the problem is not that engineers forgot to build a better radio. The problem is line of sight. If Earth-based communication is the architecture you're using, lunar rock remains very persuasive. That is almost reassuring in its honesty. Space still contains basic constraints that cannot be negotiated away with slicker software. Of course, that may not always remain the case. NASA's communications work for lunar missions includes efforts to improve infrastructure, and future relay systems could reduce or change how far-side missions experience blackout. In fact, NASA has been thinking about far-side communication challenges for decades. But for Artemis II, and for current Earth-based network assumptions, the blackout remains part of the trip. That matters because it keeps one small piece of lunar exploration resistant to the smoothing effect of convenience. Not everything is live all the time. Not every moment can be shared instantly. Some parts of spaceflight still happen in genuine separation, and only become public once the spacecraft comes back into view. There is something almost healthy about that, though healthy may not be the first word astronauts reach for in the moment. We live in a culture that often mistakes constant connection for constant control. The blackout reminds us those are not the same thing. Mission control does not control Orion by continuous conversation alone. The spacecraft works because of preparation, design, engineering margins, procedures, and the crew's own capability. In the blackout, all of that becomes exposed. The support of Earth is still real, but it has been pushed earlier in time into planning and preparation rather than live dialogue. You do not cross the far side safely because someone keeps talking to you. You cross it safely because the mission was built to survive not being talked to for a while. That may be one reason the blackout lands so strongly in the imagination. It concentrates the whole meaning of deep space travel into a short span. For those minutes, the crew is not just away from Earth. They are functionally beyond Earth's immediate conversational reach. The moon does not only separate locations, it separates voices, and because the event is temporary, it has a clear emotional arc. You know contact will return. You know signal reacquisition is expected. But during the interval, there is no halfway version of contact to soften the reality. You're either in the loop or you are behind the moon. And perhaps that is what makes the blackout such a powerful part of the Far Side story. It turns the moon from scenery into circumstance. As long as communication flows normally, the moon can still feel like an object outside the window, impressive but external. Once the signal stops, the moon becomes active in the mission in a different way. It is now the reason Earth cannot speak to the crew. It has inserted itself into the human relationship between spacecraft and planet. In that moment, the far side is not just being observed, it is shaping the conditions of observation. For a crew, that silence must sharpen awareness of the basics. The cabin, the procedures, the readouts, the other people on board, the view, the understanding that every reassuring voice, every familiar person, every city, every ocean, every ordinary sound on Earth is on the wrong side of the moon for a little while. That does not have to produce fear in a dramatic sense. It can produce focus, discipline, and even awe. But it undeniably produces perspective. You become aware, in the cleanest possible way, that spaceflight is not an extension cord from home. At some point it becomes its own room, and you're inside it. And that is exactly why the communications blackout matters so much to the larger meaning of Artemis II. It is not only a technical interval, it is one of the mission's most human moments, because it shows what lunar distance feels like when support systems are still working perfectly and yet Earth itself has gone quiet. And that is where the mission stops being only a story about the moon and becomes a story about people. Artemis II is not just another lunar flyby on paper. NASA describes it as a roughly 10-day mission around the moon and back, the first crewed lunar flyby in about 50 years, and the first time since Apollo 17 in 1972 that humans departed Earth orbit for the moon. Those are big historical statements, but underneath them sits a much simpler truth. 4 people climb into a spacecraft, leave the region where human spaceflight has mostly remained for generations, and head toward a place far enough away that Earth begins to feel less like the environment around them and more like the destination they hope to see again. One of the clearest ways NASA framed that reality was by pointing out that Artemis II would take humans beyond Earth's magnetosphere for the first time in over half a century. That may sound like the sort of line usually reserved for posters and documentaries, but it is deeply practical. The magnetosphere is part of Earth's protective environment, helping shield us from charged particles streaming from the Sun. When Orion leaves that protective region, the mission enters a less sheltered kind of space. The farther the crew travels, the more obvious it becomes that going to the moon is not just a scenic drive to a nearby object. It is a temporary departure from the protective systems of Earth itself. Distance is not measured only in miles. It is also measured in how many layers of home you have left behind. That is part of the human reality of lunar distance. The moon is close in astronomical terms, but human bodies do not care much about astronomical terms. To a person sitting inside Orion, it is not only 250,000 miles away. It is far enough that rescue is not casual. Communication can disappear behind the moon, radiation shielding matters, and the spacecraft becomes its own small world. That is a very different mental frame from life in low Earth orbit. In low orbit, astronauts are still in a highly trafficked neighbourhood of space, close enough that Earth remains visually large and operationally immediate. Around the moon, that closeness is gone. The mission becomes less like camping in the backyard and more like heading out beyond the lights, where the road signs stop appearing so often. NASA's training descriptions make it clear that this is not lost on the people preparing the crew. Artemis II's chief training officer described the process as all risk mitigation, and the point of that training is not just to memorize procedures, but to prepare the crew and flight controllers for what they might actually encounter. That phrase, what they might encounter, does a lot of work. It includes the expected things, systems operation, timelines, emergency procedures, navigation, recovery practice. But it also quietly acknowledges something harder to train for fully, the lived sensation of being that far away. NASA can simulate many aspects of the mission on Earth, but as Artemis II's training team has said, they still have gravity down here, and that means the crew must use experience and imagination to bridge the gap between mock-ups and reality. That gap matters because no training environment can fully reproduce the emotional texture of lunar distance. You can rehearse systems failures. You can practice recovery operations. You can run simulations until everyone in the room knows which switch to reach for while half asleep. But at some point, 4 actual people still have to go do the actual mission. They have to leave Earth orbit, look out the window, feel the time delay and the separation, hear the voices from home change in meaning, and understand with their bodies that the planet below is no longer below. That transition is not a failure of simulation. It is simply the fact that exploration contains first-person experiences no Earthbound rehearsal can completely fake. And because Artemis II is a crewed test flight, the human part is not secondary to the engineering. It is one of the mission's core purposes. NASA says the flight is meant to confirm the systems necessary to support astronauts in deep space exploration, and prepare for sustained presence near and on the Moon. That means the test is not just whether Orion can fly, navigate and communicate. The test is whether a real crew can live inside that system, work inside it, interpret the environment around them, and return with useful operational knowledge. Hardware is being tested, yes, but the combination of hardware and human beings is the real system under examination. The Moon is not just an objective, it is a proving ground for the human-machine partnership that later missions will depend on more heavily. This is one reason NASA introduced Artemis II science officers for the mission. The agency described these new roles as pioneering a new era of mission operations by integrating scientific skill directly into real-time support for the crew and the observations being made. That may sound like an operations detail, but it reveals something important about the human reality of lunar distance. NASA is not sending a crew just to endure the trip and come home with nice pictures. It is building a mission architecture that treats human observation, scientific interpretation, and operational awareness as intertwined. The farther humans go, the more valuable trained human judgment becomes, because a crew can notice, compare, prioritize, and describe things in ways that enrich the return from the mission. That brings us to a less glamorous truth. Deep space missions are still daily life in a machine. Even when the destination is extraordinary, someone still has to manage routines, check systems, deal with limited space, eat, sleep, maintain hygiene, and function as a small social unit in a confined cabin. NASA's own mission recaps have not shied away from this. The agency's post-flyby audio coverage included references to ordinary onboard troubleshooting, right alongside the historic language about distance and the Moon. That is fitting, because the human reality of lunar distance is not grand feeling every minute. It is awe mixed with routine, history mixed with checklist, vastness mixed with the deeply unromantic need to keep life support, sanitation, and cabin operations working. In that sense, space exploration remains refreshingly human. We go to the edge of the familiar and still have to manage the plumbing. Confinement changes the experience too. Orion is not a spacious cruise liner with panoramic lounges and a tasteful coffee corner. It is a spacecraft. Every action is shaped by limited volume, procedure, and awareness of the systems around you. On Earth, discomfort often comes with easy escape. You can take a walk, change rooms, or open a window. In deep space, the room is the window, the floor, the ceiling, and the vehicle that gets you home. That gives even ordinary moments a different weight. A spacecraft on a 10-day lunar mission is not just transportation. It is habitat, shelter, workstation, refuge, and lifeboat all at once. The farther you get from Earth, the less theoretical that becomes. There is also the social reality of being only 4 people in a very unusual place. Artemis II carries NASA astronauts Reed Wiseman, Victor Glover, and Christina Koch, along with Canadian Space Agency astronaut Jeremy Hansen. A crew this small is not just a team in the abstract, it is the entire human community on board. Every conversation, every silence, every joke, every correction, every sign of fatigue and every moment of shared observation matters more because there are so few people available to absorb the mood. In a larger setting, social energy can disperse. In a spacecraft, it tends to recirculate. That makes crew compatibility and discipline more than pleasant traits. They become part of mission design. The emotional tone of the mission, though, is not just tension. That would be too simple and not very true to how people usually experience demanding things. NASA's Artemis II coverage and related audio have emphasized not only technical accomplishment, but also the crew's own descriptions of the Moon, their messages about humanity, and the sense of unity that came with seeing Earth from so far away. That pattern should not surprise us. The farther you travel from Earth, the harder it becomes to maintain the illusion that the world below is naturally divided into separate little stories. At lunar distance, Earth is one thing, one visible world, one shared place. A crew coming back from that view often returns with a more compressed sense of what matters. What I think is especially striking is how lunar distance changes the ratio between abstraction and feeling. Before launch, the moon can still be treated as a mission target, a line item, a destination in a slide deck. During the mission, especially once Earth begins to look smaller and the blackout behind the moon approaches, the trip stops being a concept and becomes an environment. This is true for the crew, but it's also true for those watching from Earth if they are willing to pay attention. The moon is not just a dot on a trajectory plot. It is far enough away to make silence real, radiation relevant, procedures indispensable, and small acts of human steadiness unexpectedly moving. The distance is measured by how much it changes the meaning of ordinary things. Even the return from such a mission says something about the human side of it. NASA's splashdown coverage framed Artemis II as a record-setting journey that returned the crew safely to Earth after nearly 10 days. That safe return is not merely the happy end of a story, it is part of the point. A crewed test flight exists to prove not just that people can go, but that they can go, work, observe, adapt, and come home. And come home gains a different kind of emotional density after lunar distance. Home is not just where the mission ends. It is the thing that was visually reduced to a bright world in the black for a while, and then regained in full human scale at splashdown. Another aspect of the human reality is that Artemis II lives in the long shadow of Apollo without simply repeating it. NASA repeatedly describes the mission as the first return of humans to lunar space since Apollo 17 in 1972. That invites comparison, but it also creates a burden. The crew is not just travelling around the moon. They are doing so in a historical frame people already care about, compare against, and emotionally invest in. Every mission after a famous one carries that weight. Yet for the crew inside Orion, history does not reduce the need to be present. The vehicle still has to be flown, the observations still have to be made, the cabin still has to be lived in. In that sense, lunar distance is wonderfully democratic. It does not care whether the mission is legendary before launch. It asks the same practical questions of everyone who goes. There is also a quieter point that NASA's training language hints at. Artemis II training is about risk mitigation, because risk cannot be removed, only managed. That is a very adult way to think about exploration, and it is probably the healthiest one. The human reality of lunar distance is not romance stripped of all danger, nor danger stripped of all meaning. It is a disciplined acceptance that worthwhile things can be both difficult and beautiful, and that preparation is how you earn the right to experience the beauty without being destroyed by the difficulty. Spaceflight is full of magnificent visuals, but the human substance of it lives in training, teamwork, repetition, and the ability to stay useful when the environment refuses to become convenient. That is why the mission's humanity cannot be reduced to simple inspiration. Inspiration is there, certainly, but so are uncertainty, discipline, fatigue, and the effort of remaining steady while crossing a place where Earth is visibly far away. The crew has to perform while carrying the emotional knowledge that they are outside the usual shelter of the planet, outside the comfort of instant contact during farside passage, and inside a machine that must keep working because there is nowhere else to go. That combination makes the mission compelling in a deeper way than slogans ever do. It is not merely that brave people go to the moon, it is that ordinary human needs, emotions, and limits have to travel with them and somehow function in that setting. And because of all this, Artemis II gives us something rare. It lets us watch the meaning of lunar distance pass through actual human beings, rather than staying trapped in simulation or historical memory. We get to see what kind of observations matter to them, what kinds of feelings survive the procedures, and what changes when the crew looks back at Earth after seeing the far side. Those changes may not always appear dramatic in posture or expression. Often they emerge through word choice, through pauses, through the kinds of details astronauts bother to mention. Space does not just test equipment, it edits attention. After lunar distance, certain things seem more essential and other things shrink, which is why the next question becomes so important. Once a crew reaches that distance, crosses behind the moon, and looks out at a world cameras can record but not fully feel, what exactly do trained human beings notice that a lens alone does not? Cameras are wonderful, and it would be silly to pretend otherwise. They freeze moments, preserve evidence, let scientists compare views years later, and allow the rest of us to join a mission we are not physically on. Artemis II carries handheld cameras and is built to return high-resolution imagery of the lunar surface, including regions of the far side humans had not directly seen before. NASA has been very explicit about the importance of those images, but NASA has also been equally clear about something else. One of the most powerful scientific tools on Artemis II is not a sensor package or a lens. It is the 4 pairs of human eyes on board. That is not a sentimental line added to make exploration sound noble. It is a recognition that trained human observation does something cameras alone do not fully do. NASA even built formal preparation around that fact. The Artemis II crew trained to observe key lunar features, practiced with the same sorts of handheld cameras they would use in flight, and worked with science teams on how to describe what they were seeing. NASA's Observe the Moon Like an Astronaut materials note that the crew prepared on a set of important lunar targets, and that at closest approach, the moon would appear roughly the size of a basketball held at arm's length through Orion's window. That detail is helpful, because it reminds us this is not a telescopic view from a backyard. The astronauts are close enough for texture, relief, and relationships between features to matter in a very immediate way. They are not simply looking at a disk. They are looking at landscape from nearby. Now, the obvious response is, yes, but isn't a good camera better than an eye? For some tasks, absolutely. A camera can zoom, store, compare, and preserve. It can feed later analysis with a level of consistency memory cannot match. It can also see things the eye cannot, especially when paired with filters, long exposures, or other instrumentation. But human seeing is not just about resolution, it is about context. A trained person can shift attention in real time, compare adjacent features instantly, notice unexpected patterns, decide what is worth lingering on, and describe the scene with a sensitivity to depth, lighting, and relationship that a frozen image can reduce. A camera records what is in front of it. A person notices what is strange about what is in front of it. Those are related but not identical skills. Lighting is one of the best examples. NASA's lunar mission agenda pointed out that the sun's angle on the moon changes the visibility of features in significant ways. If the sun is high, there are fewer shadows, and the crew has to pay attention to subtle changes in surface brightness and colour. If the sun is low, long shadows reveal relief, steepness, crater rims, and texture much more clearly. The exact lighting conditions during a flyby are not fixed in a neat, perfectly staged way months in advance. They depend on launch timing and orbital geometry. A camera will record whatever illumination it gets. A trained astronaut, by contrast, can respond to that illumination, change where they look first, notice which features have become more legible, and adjust observation priorities on the spot. NASA's released Artemis II images make this point very nicely. One close-up view of Vavilov crater on the rim of the older Hertzsprung basin highlights how long shadows at the terminator accentuate the crater, its ejecta, and the transition from smoother terrain to more rugged ground. That is a beautiful scientific image. But the human observer looking at that same scene in motion, through changing geometry, does not just receive a single frame. The eye and brain get depth cues, evolving shadow relationships, an immediate comparison between one feature and the next. The human observer can feel how relief organizes the terrain. A still image can suggest that. A person looking out the window can experience it. Depth is one of the things cameras are surprisingly bad at communicating cleanly, unless everything goes exactly right. A photograph flattens. It can be spectacular and still flatten. It turns a three-dimensional scene into a two-dimensional surface and then asks your brain to reconstruct volume from lighting, overlap and perspective. Human eyes looking directly at the moon through a spacecraft window have an advantage here. They are part of a moving body in space. The observer can track how shadows slide across terrain, how crater walls relate to surrounding plains, how one basin sits inside another, and how the edge of a mountain ring changes as the spacecraft's angle changes. The camera gives you a beautiful piece of evidence. The observer gets a sequence of embodied impressions that no single frame can fully contain. Motion matters in another way too. Artemis II's science observations were not designed as passive sightseeing. NASA's simulation and preparation materials show that the flyby involved a defined period of observations over several hours, during which the crew would watch the moon under changing conditions. A person observing over time can link one view to the next. They can notice what emerges as the angle changes. They can detect where a smooth interior transitions into rougher terrain, where one basin's history seems to cross into another's, or where colour differences begin to stand out once relief becomes easier to pass. A camera can certainly record time series, but it still depends on someone later deciding what to compare and why. A trained astronaut can do that comparison while the scene is alive in front of them. There is also the issue of surprise. Cameras are excellent at documenting what you aimed them at. Humans are excellent at noticing what no one expected. NASA specifically planned for Artemis 2 astronauts to watch for impact flashes from meteoroids striking the moon. Those flashes are fleeting, rare enough to be scientifically useful, and best seen under the right lighting conditions. An automated system might miss something outside its programmed priorities. The human observer with context can notice a brief flash, judge whether it is meaningful, cross-check with the scene, and call it out immediately. Even when cameras catch such events, it is often the observer who gives the moment significance by recognizing that something unusual has happened at all. The same is true for scale and orientation. A camera image can show you a crater or basin, but it often struggles to tell you how the scene felt spatially to someone in the cabin. Was the terrain visually crowded or surprisingly open? Did one ridgeline stand out in a way the maps did not prepare you for? Did the surface feel more broken, more jagged, more varied in brightness than expected? NASA's emphasis on astronaut observation during Artemis II suggests that these are not trivial extras. They are part of the mission's scientific value. Human beings are very good at noticing gestalt, the whole pattern of a scene, in ways that are difficult to reduce to a single raw image file. Then there is the simple matter of field of view. A camera always frames. That is its job. Framing is useful because it forces attention and produces data that can be archived and studied, but framing also excludes. A human observer can hold both the detailed target and the wider scene in mind at once. They can look past the crater they were assigned to study and notice how it sits in a larger terrain context. They can switch from narrow attention to broader orientation without changing lenses or waiting for a later stitch of many images. NASA trained the Artemis II crew with multiple lenses for the lunar flyby, including wide and zoom options, which is telling. It is an acknowledgement that no one view is enough. Human seeing stitches those scales together almost effortlessly. A camera also has no feeling for importance. It can be pointed at something important because a human decided it was important. That distinction matters more than it sounds. When NASA says Artemis II science officers are helping integrate lunar science operations, it is because the mission does not simply want pictures. It wants pictures guided by priorities, judgment, and scientific attention. A human observer can decide that a subtle transition in terrain matters, that a shadowed wall deserves another look, or that a fleeting event should alter the observation sequence. Cameras are tools. Observation is an activity. The difference is easy to overlook until you remember that the most famous images in spaceflight history were not created by machines deciding what mattered. They were created by people noticing. Emotion is part of this too, and not in a vague or purely artistic way. Emotion changes what people attend to. It changes how long they linger, what they compare, what they remember, and how carefully they describe a moment afterward. NASA's Earth Observatory coverage of Earthset from the lunar far side is a perfect example. The image is extraordinary, but the meaning of Earthset is not reducible to pixels. To the crew, Earth was not merely a bright object crossing the frame, it was home moving below the lunar horizon while communication was already becoming an issue. A camera can preserve the image of that moment. It cannot preserve the crew's full understanding of what the moment meant while it was happening. That meaning comes back to us through human description. The same goes for Earthrise after the blackout. NASA's flight day coverage noted the crew witnessed an Earthrise as Orion emerged from behind the moon. Again, a camera can capture the event beautifully. It may even capture it more sharply than the eye remembers. But the camera does not know that the image arrives after 40 minutes of silence. It does not know what the return of Earth to view means in the body of someone who has just crossed behind another world. It does not know relief, awe, or the strange compression of seeing an entire planet become a visible object again. Those are human layers placed on top of the visual fact. And because astronauts are trained observers, those human layers are not noise contaminating the science. They are part of what makes the mission richer. This is not a case against imaging. It is a case against pretending imaging is the whole of seeing. NASA has invested heavily in visualization, simulations, and observation planning for Artemis II, precisely because images matter so much. The mission simulations show what the crew would see out the window along the actual flyby path. NASA adapted crew Earth observations techniques for Artemis II, so astronauts could use handheld cameras effectively in a deep space setting. These are serious, deliberate efforts to get the best possible visual record, but all of them assume something important, that there are benefits to having people in the loop, because people can respond to the scene rather than merely receiving it. Human observers are also good at integrating imperfect information. If part of a scene is blown out, if glare changes, if the light is awkward, if a window edge intrudes, if one feature is more visible in peripheral view than straight on, a person can still make sense of the whole. Cameras, especially handheld ones used under time pressure, have their limits. Exposure settings, motion, window reflections, and available framing all affect the result. NASA's mission materials make clear that the crew was carefully trained in camera use and cabin choreography and microgravity, which again tells us something. Getting the image is not automatic, it takes practice. The human observer, meanwhile, continues seeing even when the image is not perfect. There is also an honesty in admitting that some things are simply easier to understand in person. The moon's far side is famous for being rougher, older, more cratered, and geologically more difficult to summarize than the near side. Looking at photographs of it is informative. Moving past it in a spacecraft with changing illumination and an awareness of scale is another level of comprehension. You can know from a map that the terrain is heavily cratered. You can know from a scientific paper that the crust is thicker. But the human eye, faced with the actual density of overlapping scars and the way light moves across them, can arrive at a more immediate kind of understanding. That kind of understanding is not more rigorous than later analysis. It is more direct. This is why astronauts have so often been described as both subjects and scientists. NASA used exactly that language for Artemis II in the context of deep space research. The crew is not only being observed for human health and performance, they are participating in the act of observation itself. Their bodies, minds, attention, and judgment are all part of the mission. That dual role matters because it tells us the point of sending humans is not just symbolism. It is that humans are unusual instruments. They are imperfect, emotional, limited, and yet astonishingly flexible in the presence of the unexpected. The moon is not only being photographed, it is being encountered. There is one more point I think matters. A camera cannot come home changed. It can come home full of frames, data, and extraordinary evidence, but it does not return with a revised sense of Earth or a different understanding of fragility. Astronauts do. They do not just bring back images. They bring back interpretations shaped by being there. That is why their observations matter even when the photographs are stunning. The photographs show us what they saw. The astronauts tell us what it was like to see it. Those are not competing outputs. They are two halves of the same gift. And once the eye turns away from the moon and finds Earth, the whole mission changes shape again. Up to that point, the far side can still feel like the main story. The craters, the shadows, the ancient basins, the blackout, the scientific puzzles. Then Earth appears, or disappears, and the emotional centre of gravity shifts. NASA's recent Earth Observatory coverage of Artemis II described Earthset from the lunar far side, captured by the crew during their journey around the moon. That phrase alone is enough to stop you for a moment. Earthset. We're so used to speaking about sunset or moonrise that the word feels slightly improper, as if language is telling us we have wandered into a place human beings were not originally built to narrate. But there it is, our whole world slipping behind the lunar horizon, becoming a visible object in someone else's sky. NASA's image description for that Earthset is wonderfully specific. It describes a muted blue Earth with bright white clouds setting behind the cratered lunar surface, with the dark part of Earth in nighttime and the sunlit side showing cloud patterns over Australia and Oceania. In the foreground sits Ohm Crater, with terraced edges and central peaks. That is a real image, a real angle, a real moment. But even in that careful description, something larger is happening. Earth is no longer the place where the mission is being watched from. It becomes a distant body with weather, colour, day and night, and a fragile, almost decorative appearance against the severe rock of the moon. The camera captures the scene. The mind then has to cope with what the scene means. Beauty comes first because it usually does. Earth from lunar distance is beautiful in a way that is almost unfair. The moon is grey, dry, cratered and stark. Earth is blue, white and visibly alive with motion in its atmosphere. Clouds curl around it. The sunlit edge glows. The colour difference alone is enough to make the planet feel improbably precious. You do not need to know anything about biology, climate or planetary chemistry to feel the contrast. One world looks like it can host oceans, breath, birds, moss, rain and conversation. The other looks like what remains when those things never got a chance or lost their chance long ago. Beauty in that comparison is not superficial. It is a visual summary of habitability. Then fragility arrives a moment later, because beauty at that distance is inseparable from smallness. NASA notes that Artemis II reached a maximum distance of 252,756 miles from Earth during the lunar flyby, farther than any humans had gone before. At that distance, Earth does not dominate the sky. It becomes a contained thing. A world, yes, but also a sphere you can look across with your eyes rather than with your imagination. That shift is psychologically important. On Earth, we experience the planet as enormous because it surrounds us. From far away, the same planet becomes finite. Once something looks finite, it also begins to look vulnerable. This is one of the strange gifts of spaceflight. It can make the most familiar thing in your life feel newly contingent. Down here, Earth often feels functionally indestructible because our scale is wrong for the question. We think in neighbourhoods, roads, storms, countries, screens, deadlines, and sometimes whether the laundry made it out of the machine. At lunar distance, the scale resets. Earth is no longer a backdrop too large to perceive. It is an object too small to ignore. You see at once that it is wrapped in a thin atmosphere, carrying surface water in a black environment that offers no obvious substitute, and alone in a way that can be intellectually understood from textbooks, but not fully felt until you see it suspended like that. That is where the shock enters. Not because Earth looks ugly or wounded from afar, but because it looks singular. There is no second Earth beside it to reassure the eye, no backup copy, no replacement humming quietly just out of frame. The moon does not produce that reaction simply by being near Earth. It produces it by contrasting so harshly with Earth. The far side of the moon is ancient, dry, cratered, and silent. Against that foreground, Earth becomes not just beautiful but improbable. You begin to understand home as a rare planetary condition rather than a default one. That realization does not always arrive theatrically. Sometimes it lands as a quiet pressure in the chest, sometimes as gratitude, sometimes as a kind of grief for how casually we often treat the place. NASA's own history gives us a useful precedent here. The famous Earthrise image taken during Apollo 8 quickly became a symbol of unity and a new way of seeing our planet. NASA's Only on Earth coverage explicitly describes that photograph as a powerful symbol of unity. Artemis II does not replace that legacy so much as extend it. When the crew captures Earthset and then experiences Earthrise again after emerging from behind the moon, they are participating in the same deep correction of perspective. The moon stops being only a destination and becomes a platform from which Earth can be reintroduced to human beings in the proper scale. One world, one habitat, one place where every argument and every love story are somehow happening at once. The far side intensifies this because Earth is not continuously present in the window. NASA's mission updates describe both Earthset during the blackout phase and Earthrise as Orion re-emerged from behind the moon and communication was restored. That sequence matters. Earth is seen, then lost, then seen again. And during the loss, the crew is also out of contact with the people back home. The effect is not just visual but relational. Earth goes from being a visible world to being hidden and silent, to returning as both sight and connection. That is a powerful emotional arc compressed into a short segment of flight. A camera can document each stage. A human being on board experiences the continuity between them. One reason this view hits so hard is that Earth from the far side is not merely pretty. Pretty is what you say about a postcard or a lake at the right hour of evening. Earth from lunar distance is more destabilizing than pretty, because it compresses scale and value into one visual fact. You see all the cloud systems, all the oceans, all the continents, all the people, all the languages, all the history, all the food, all the wars, all the lullabies, all the hospitals, all the funerals, all the weddings, all the coral reefs, all the library books, all the traffic, all the kindness, all the stupidity, all the ordinary Tuesday afternoons on one sphere. And suddenly the phrase, the good Earth, which can sound almost quaint on the ground, starts to feel like a sober description rather than a sentimental one. The beauty, then, is inseparable from limits. The white cloud bands are beautiful because they belong to an atmosphere of limited thickness. The blue is beautiful because liquid surface water is not a normal everyday property of rocky worlds in our immediate visual comparison. The brightness is beautiful because it is life-friendly chemistry made visible, and the shock comes from realizing how narrow the margin may be. If you stand on Earth, it is easy to imagine habitability as the stage on which life plays out. From near the moon, habitability becomes the main performance. Everything else is secondary. The atmosphere is no longer background. It is one of the stars of the show. There is also a moral sharpness to the view, though that does not need to turn preachy to be real. When Earth is seen from far away, the categories that occupy us so intensely at ground level become hard to locate. Borders are not visible in the way they are on maps. Property lines do not appear. Neither do currencies, elections, reputations, or comment sections. This does not make politics unreal or daily life unimportant, but it does expose their scale. Human concerns are real, yet many of them look newly local from lunar distance. What does not look local is Earth itself. That whole blue and white sphere is carrying every national project and every private sorrow at the same time. A view like that does not automatically make people wise, but it does make narrowness harder to defend with a straight face. NASA's recent Artemis II audio and mission coverage hinted at this broader emotional effect by emphasizing the crew's unifying message for humanity alongside their technical observations. That pairing feels exactly right. The mission is not either scientific or humanistic. It becomes both at once because the science carries the humans to a place where their categories change. The crew goes to observe the moon, and in doing so, they also become witnesses to Earth, in a way very few people ever have. It would be stranger if they did not come back talking about unity, fragility, and shared home. The view almost demands that language. There is something else that often goes unnoticed in discussions like this. Shock is not always fear. Sometimes shock is the sudden collapse of a bad habit of thought. On Earth, many of us move through life with the unexamined assumption that our world is the normal kind of world. The moon contradicts that. The far side of the moon contradicts it very efficiently. Dry stone, impact scars, silence, no atmosphere to soften the light, no seas, no forests, no weather worth the name. Then, in the same field of awareness, there is Earth. The contrast is so strong that it can be cognitively rude. It interrupts the assumption that life-friendly conditions are standard equipment. The shock is not how frightening, it is how unusually fortunate. That fortune can also feel heavy. Fragility is not always comforting knowledge. To see Earth as singular is to feel affection for it, but also responsibility. A lot of people prefer cosmic imagery when it is humbling in a vague, soothing way. The Earth from the moon view is more demanding than that. It does humble, yes, but it also confronts. It says, here is the only visibly living world in your immediate human story, hanging there against black space, and you are all on it together. There is no clever way around that fact. The planet is not a symbol first. It is a system keeping everyone alive. The image is beautiful because the system works. The fragility is shocking because the system is finite. And the moon, oddly enough, helps tell that truth with unusual clarity, precisely because it is so different. If Artemis II had flown past a world that looked lush, wet, and cloud-covered itself, Earth might have looked less singular by comparison. But the moon is a severe neighbour. It makes no effort to flatter us. Its far side is older, drier, more heavily cratered, less volcanic in broad terms, and geologically harder. That severity strips Earth of any false sense of redundancy. You're not looking from one comfortable world to another. You're looking from a hard world back at the one soft enough to have raised you. The moon becomes the frame that makes Earth legible. This is where grief can quietly enter the picture. Not grief in the tragic sense necessarily, but grief in the sense of finally seeing the value of something you are used to treating as given. People often report that distance makes them appreciate home. Lunar distance may do that at the highest useful intensity. The view of Earth does not just make home seem dearer, it makes home seem less replaceable. That can be painful in its own calm way, because once you really see that, a lot of our casual damage and waste begin to look less like unfortunate side effects, and more like insults to a miracle. Again, there is no need to become grand about it. The image itself is already doing enough work. There is a practical lesson hidden in all this emotion too. Artemis II is a test flight for future missions, including missions that will keep people in deep space longer, and perhaps one day take them to Mars. If Earth from lunar distance already has this effect, then the emotional lives of crews are not side issues. Perspective is part of exploration. How astronauts process isolation, wonder, risk, and attachment to home matters. Their changed understanding of Earth is not a decorative afterthought to the mission. It is one of the things the mission produces. Spaceflight does not just move bodies. It can rearrange the hierarchy of what feels important. And perhaps that is the real reason the Earth view matters so much. It takes all the dry facts of the mission, distance, trajectory, shielding, observation, blackout, training, and converts them into a single visual answer to a human question. What exactly are we leaving when we leave Earth? The answer is not a launch site or a planet. The answer is weather, water, breath, ecosystems, families, memory, language, colour, and a world complicated enough to be irritating and beautiful at the same time. The farther away that world gets, the harder it becomes to pretend it is ordinary. So yes, Earth from the far side of the moon is beautiful. But that is only the beginning. It is beautiful in a way that exposes fragility, and fragile in a way that creates shock, and shocking in a way that can leave a person calmer, sadder, wiser, or all three at once. The image of Earth against black space does not flatter us. It clarifies us. It says, without raising its voice, that whatever else humanity is arguing about, it is all happening inside one thin atmosphere on one bright sphere that looks very small from not very far away. By the time you reach this point in the journey, the moon has stopped behaving like a simple object. It is no longer just the thing that pulls the tides, brightens the night, and appears reliably outside the bedroom window. It has become a place with two very different faces, a place where geology explains mystery without removing it, and a place where a crude flyby can turn science into a deeply personal experience. Artemis II matters, partly because it tests systems for deep space exploration and helps prepare for future missions. But the mission matters just as much because it shows that the farther we travel from Earth, the harder it becomes to think of exploration as merely collecting data. At some point, exploration starts collecting us too. That is what I mean when I say the moon becomes a mirror. Not a literal mirror, of course. It does not reflect back a neat image with convenient lighting and flattering angles. It reflects us in a harsher way. It shows us what we assume without noticing. It shows us how much of our sense of normal depends on air, water, warmth, weather, and constant connection. It shows us how quickly the familiar can become precious once it is framed by something airless and old. The far side of the moon does not lecture. It simply offers contrast, and contrast, when it is strong enough, can become revelation. For most of human history, the moon was a symbol. It still is in many ways. People have used it to measure months, guide travel, write songs, decorate stories, and make meaning out of darkness. But once humans begin travelling around it again, especially around its hidden hemisphere, the symbol grows sharper and less forgiving. The moon becomes a real place in the full sense. It has a thick far-side crust, a rough impact history, a communication geometry that cuts you off from Earth for a while, and a surface that reminds you the solar system did not become gentle just because we got used to it. Artemis II puts humans back into relation with that reality. The mission gives the moon enough presence to stop being merely poetic, and that is useful because symbols are often too easy. A symbol can be loved without being understood. A real place has to be dealt with. The far side of the moon forces that dealing. It is older, more cratered, less volcanic in broad appearance, and geologically more difficult than the near side. It blocks communication during flyby. It withholds the easy comfort of the familiar Maria. It reminds us that what we see from Earth is only part of the story. In that sense, the moon mirrors one of our oldest habits, mistaking familiarity for completeness. We think we know something because we know its public face. The far side is what corrects that mistake. The journey changes us because it changes the scale at which our assumptions operate. On Earth, we are large enough relative to our surroundings that our dramas feel central. Even when we understand astronomy in a textbook sense, daily life keeps resetting the scale back to something human-sized. The moon interrupts that, not because it is the most extreme place in the universe, but because it is close enough to reach and different enough to expose the specialness of home. That combination is unusually powerful. A place does not have to be infinitely distant to transform perspective. It only has to be far enough, silent enough, and severe enough that the return view of Earth becomes impossible to misread. This is why the far side is so important to the mission's meaning. The blackout behind the moon, for instance, is not just a communications detail. It is a lived lesson in dependence and preparation. Earth does not vanish forever, but it vanishes enough. The voices stop long enough. The line of sight breaks long enough. A crew can know the procedures, trust the spacecraft, and still feel the change. There is value in that. Not because fear is the goal, but because perspective is. The mission teaches, in a calm and operationally disciplined way, that some forms of security we take for granted are local privileges of being near home. The moon mirrors our biology too. Our bodies are Earth bodies. We are tuned to one gravity, one atmosphere, one chemical balance, one protective magnetic environment, and one wet world. Artemis II makes this clear by taking humans beyond Earth's magnetosphere and into a deep space environment where the spacecraft becomes the immediate world that keeps them alive. That fact can sit quietly in mission documents, but its meaning is not quiet once you imagine living inside it. The farther you go, the more obvious it becomes that human beings are not generic creatures who happen to live on Earth. We are creatures formed by Earth in fine detail. To leave it is possible. To stop needing it is another question entirely. It also mirrors our psychology. We like certainty. We like connection. We like the feeling that help is nearby, that the room is not too small, that the horizon belongs to us, and that the systems supporting our lives are so normal they do not require gratitude every few seconds. Spaceflight strips away that invisibility. In Orion, support systems are visible and finite. Air is managed. Water is managed. Waste is managed. Communication is managed. Heat is managed. Distance is managed. Life becomes legible as a network of conditions rather than a background assumption. This can be unsettling, but it can also be clarifying in a very healthy way. The moon mirrors how much human life depends on structures we usually do not notice until they are strained. And then, of course, there is Earth itself, the strongest reflection of all. From the far side, Earth becomes smaller, singular, and visually fragile. NASA's Earthset imagery from Artemis II and the historical resonance with Earthrise remind us that spaceflight changes not only what we know, but what we feel we know. The planet does not become important because astronauts say nice things about it afterward. It becomes important because distance gives our eyes a chance to see its wholeness all at once. Once that happens, it is difficult to unsee. Earth as a single, bright world in darkness is not just beautiful. It is morally inconvenient in the best possible way. It makes pettiness look smaller than it would like to appear. That is one reason missions like Artemis II matter even to people who may never care much about rocket specifications or navigation burns. The mission is scientific, yes. It is technological, yes. It is also civic in a very broad sense. It gives humanity one of the few kinds of perspective that can cut cleanly through noise. When astronauts return from deep space and speak about unity, fragility, and the wonder of Earth, they are not reciting mandatory poetry for public outreach. They are often responding to a correction in scale. The moon does not make us better automatically, but it can make some of our worst illusions harder to maintain. The moon mirrors our limitations as well, and there is something almost comforting about that if you let it be. We're curious enough to go there, but not powerful enough to turn it into a friendly extension of Earth on command. We can orbit it, image it, sample it, map it, and learn from it, yet its harshness remains, its dryness remains, its silence remains, its old scars remain. In a strange way, this is good for us. A universe too eager to yield would teach arrogance. A universe that offers understanding only through patience, engineering, and humility may be frustrating, but it teaches better lessons. The moon has a way of making competence feel noble, and ego feel slightly childish. It also mirrors the value of people in exploration. One of the themes of Artemis II is that cameras, sensors, and simulations are essential, but trained human observers still add something irreplaceable. The crew can notice, compare, react, and remember in ways that no instrument fully duplicates. That matters not only for science, but for meaning. The moon is not just being measured, it is being witnessed. And witnessing is one of the most human things there is. It involves attention, interpretation, judgment, and emotion. In that sense, the moon becomes a mirror not only because it shows us Earth, but because it reveals what kind of creatures we are when confronted with a place that exceeds our usual categories. There is a gentle irony in all this. People sometimes speak about going to the moon as though the main purpose were to understand the moon better, and of course that is part of it. But over and over again, the moon also helps us understand Earth better, and not only Earth as a planet, Earth as home, Earth as shared vulnerability, Earth as the environment that made us capable of asking questions in the first place. The moon changes us because it sits at the perfect distance for correction, far enough to transform perspective, close enough to return from, severe enough to expose the truth, and familiar enough that the contrast does not get lost in total strangeness. It is a remarkably efficient teacher. This is why the journey remains meaningful even if the far side contains no secret civilization, no supernatural threat, and no dramatic revelation in the tabloid sense. The real revelation is more mature than that. The moon's hidden hemisphere is terrifying, yes, but mostly because it is honest. Honest about impact history, honest about silence, honest about what an airless world looks like after billions of years, honest about how much of Earth's gentleness is local and precious, honest about how quickly the human mind reorders its values when the planet is reduced to a blue sphere in black space. Sensational stories would actually cheapen the lesson. Reality is already strong enough, and once you see that, the title itself changes meaning. What we found on the far side of the moon is terrifying stops sounding like a promise of monsters and starts sounding like a promise of perspective. What we found was a harsher moon than most people imagine, a landscape older and less forgiving than the face we know, a communications silence that turns distance into experience, and a vantage point from which Earth becomes both beautiful and alarming in its fragility. None of that is fictional. None of it requires embellishment. The terror, if we can call it that, lies in how plainly the far side reveals the conditions we depend on and how little of the universe is arranged around our comfort. At the same time, the mirror is not cruel. That is important. The moon does not only reduce us, it also enlarges us in the right ways. It shows what careful cooperation can build. It shows that curiosity can survive risk. It shows that scientific preparation and human courage can work together rather than cancel each other out. And it shows that people can leave Earth, look back at it from near the moon, and return with a message less about conquest than about connection. That may be one of the healthiest developments in how we talk about exploration. The farther we go, the less convincing the old language of dominance seems. The better language is stewardship, humility and wonder joined to competence. So perhaps the moon changes us because it reveals proportion. It puts human beings in scale with stone, silence and time, and it puts Earth in scale with the needs of life. It reminds us that the universe is not built for us, yet somehow here we are, able to notice that fact and be moved by it. There is something very tender in that. We are small enough to be humbled and conscious enough to care. The moon reflects both truths at once. And now, dear listener, we find ourselves where all good journeys eventually do, not only at an ending, but at a clearer view. We set out toward the far side of the moon expecting danger, mystery, and the unknown. We found those things, but we also found older rock, thicker crust, missing Maria, a colder interior story, a passage through silence, human eyes doing the work cameras cannot finish, and Earth itself looking more beautiful and more breakable than most of us are used to admitting. The moon did not just show us what it is, it showed us what we are when we leave home and dare to look back. So let me ask you, gently, one last time, where are you listening from tonight, and what time is it now where you are? Funny, isn't it, that after travelling all this way in thought, around the moon, behind it and back again, we end where we always do, in a room somewhere on Earth, under an atmosphere, inside gravity, surrounded by the ordinary miracles of warmth, pressure, breath, and home. If this quiet trip through lunar darkness gave you a little calm, a little wonder, or simply a softer place to let your thoughts settle, I'd be ever so grateful if you like the video, maybe subscribed, and shared this small sleepy corner of science with someone else who might need it. For now though, it is enough to rest with the image. A blue world in black space, a grey moon keeping its old secrets. 4 people crossing the silence and coming home with their sense of proportion changed. And you, here at the end of the journey, a little farther along in time than when we began, perhaps a little sleepier too. So wherever you are, and whenever this finds you, sleep well and keep a small place in your thoughts for that hidden side of the moon, because sometimes the strangest places in the sky are the ones that teach us most clearly how precious home really is.